Good morning, everyone. Thanks for coming to the second day of the Move Solid Mechanics workshop. For those of you who are new today, my name is Gary Hu. I'm a mechanical engineer from the Argonne National Lab. So first, just as a recap, yesterday we just introduced some fundamentals of the MOOS framework, and we covered most of the fundamental capabilities of the MOOS solid mechanics module. And today we will, well, so yesterday it was more an analyst facing, in the sense that we were mostly playing with input files to demonstrate different capabilities. So today, the workshop will be more developer facing, where I would expect everyone to be coding, basically. And my goal is that hopefully by the end of today, we will be able to use our own MOOS-based application that we created yesterday called Snail to solve phase field fracture problems. So that will be tutorials 10, 11, and 12. And for so after that, in tutorial 13, I will let everyone know how to set up your own regression testing to make sure your whatever you implement can work and can stay working, as well as some documentation strategies. I will introduce the MOOS docs system, which is a very powerful documentation tool. And then as the last tutorial today, I will spend the rest of the time going over two external material modeling strategies. So, so one of them is through Abacus UMAT. So if you're coming from, so if you're a previous Abacus user, you may have many Abacus UMAT implemented for various material models that you're interested in. And we will, I will briefly go over how to set up a material model using the Abacus UMAT Fortran file. And the second external material model library is called NEMO2, and it is a modern material modeling library developed by the Argonne National Lab. And I will basically go over the architecture of the material modeling library NEMO2, and also cover how to set up a material model using NEMO2. Yeah, so that's today's agenda. Let's move directly to tutorial 10 now. If you well, so if you missed yesterday's workshop and so you are still in the process of installing your MOOS, please let us know if you run into any issues, and we will be able to help you with any installation questions. Oh, and sorry, before we begin, there's one thing I forgot to mention yesterday. I actually left a message on Slack. So yesterday, when we were going all of the tutorials, we set up a lot of input files to demonstrate different capabilities. So we were using the physics solid mechanics syntax, right? So that is so this syntax is valid as long as you're using an up-to-date MOOS. However, if your MOOS is older than a few weeks or a month or so, you may have to use a legacy syntax, which I think is called tensor mechanics. I think I posted the syntax on the Slack workspace. It's called tensor mechanics master or something like that. So just keep that in mind. Everything else should be identical. It's just the entry point to the solid mechanics module is slightly different. And if you are using an outdated MOOS, our recommendation is to actually update your MOOS to the latest version so that we have all the newest capabilities available to you. Okay, so for tutorial 10, we will not start looking at phase field fracture right away. We will try to first learn how to implement a custom material model using the solid mechanics module. So in this case, in this example, we will use the nearly incompressible Neo-Hookean material as an example. So it is a hyperelastic material. And in our implementation, we will also be using the so-called three-field formulation to make the problem in-soup stable. And this is for Neo-Hookean material, as I mentioned yesterday, apparently you can find many different forms of the string energy density function. So for the purpose of this tutorial, let's stick with this one. This is some commonly used form that I found in the literature. So this the string energy density function is equal to K, which is the linearized bulk modulus, times a penalty function H, plus mu1 times the trace of the isochoric right Cauchy-Green strain, plus mu2 times, this is the second invariant of the isochoric right Cauchy-Green strain to the power of 3/2. So that's the form of the string energy density function. So we will not be implementing the string energy density function directly. However, typical to a hyperelastic material, we will be first deriving the thermodynamic forces corresponding to this string energy density function. And in MOOS, we will be implementing the resulting second Piola-Kirchhoff stress in our custom material. So if you take the derivative of the string energy density function with respect to the right Cauchy-Green strain, you will get the second Piola-Kirchhoff stress. So the equation is shown here. So it can be, so from the string energy density function, you can see that there is a volumetric part parameterized by the bulk modulus, and there is also a isochoric part characterized by these two parameters, mu1 and mu2. And as a result, the second Piola-Kirchhoff stress can be decomposed into a volumetric part and a isochoric part as well. So for so for the isochoric part, I think in the boilerplate code, I have implemented that for you because it's not the focus of our tutorial. For the volumetric part, we will be implementing together. And for the regarding three-field formulation, we need to introduce two additional auxiliary field, namely P and theta, where P represents the hydrostatic stress and theta represents the volumetric dilation of the current element. And in order for the purpose of stabilization, we will be choosing P and theta from a piecewise constant function space. And so we can perform the standard static condensation procedure to make the formulation more stable. And so we will first go over the first step of this formulation, which is the static condensation. Well, effectively, what it does is it's basically computing the volume average of it's computing the element average of the Jacobian and the element average of the hydrostatic stress. There's nothing complicated with regarding these two auxiliary fields. So let's get started. Well, any questions so far? I mean, the theory is probably a little involving, but when we actually go to implement that, I think it's fairly straightforward. So when you open a new terminal, don't forget. Well, let me make the terminal larger. So when you open a new terminal, don't forget to activate your Moose environment. So that's, I think it's Conda activate Moose. If you followed our instructions yesterday, I mean, for me it's because that's my alias. Okay, so for the development today, I will be using VS Code. If you're using a different editor, you probably need to figure out how to do auto formatting and auto completion on your own. But for VS Code, I will make some recommendations as to which extensions we're going to use. Yes. Do you use Clang by any chance? Do I use Clang for an extension? What? If you don't know, I'm just curious. So a lot of the auto format packages need a compile command JSON for auto linking. If you're not familiar with it. Yes. Well, what's the name of the extension? The third one. The third one? What does it do? It does a lot of auto format linking when you're coding source code. It's nice. You just need to generate a compile command. Oh, I think, yeah, for the go-to definition thing, you need to first generate the tags in order for a cross-reference to work, I think. I don't know. I haven't used it yet. Yeah, I mean, I'm sure someone has used this. So, okay. I mean, I can try to figure it out and get back to you. Yeah, it seems to be a powerful extension. But I mean, well, so for the purpose of this tutorial, I will just recommend this extension, the called CLAN format. It's as long as you have a CLAN format installed in your Moose environment, well, which comes by default, you will be able to format your code. That's mostly what I will rely on today. Okay, so for this, well, this is tutorial 10, right? So we will create a header file called tutorial 10 stress.h and a corresponding source file called tutorial 10 stress.c. Is the font large enough for that, or I need to make it larger? It's okay. Okay, how do I make it larger then? How about this? Okay. Okay, so in tutorial 10 stress.h, so that's the header file. I've populated most of the code for you already, but let's first go over what they do. So first of all, when you implement a custom material, you need to inherit from well, the material base class. So that will expose a lot of common APIs to you. And I will go over which of the interfaces we need to override in just a moment. And then any other necessary includes. So in this case, our Piola-Kirchhoff stress and the deformation gradient and things like that will all be ranked through tensor. And so here I'm including that as an additional header. And then in your custom material, if you need to use other data structures or other functions, this is where you need to include your additional headers. And then here, since we want to implement a custom material, we need to inherit from the base material class. So if you've taken a C++ course, this is how you do class inheritance. There's so these two methods we've already seen yesterday. So the first one defines the expected input file parameters. So remember, MOOS serves as the bridge between developers and analysts, and so there has to be a way for the developers to tell the analysts what to include in the input file. So that's what this method is doing, right? And then the second method is a constructor. It takes a set of input parameters extracted from the input file and then tells MOOS how to construct this object. And so this is the other way back, taking that bridge. So it's basically this is basically telling MOOS how to construct your custom object based on the information provided by the analysts inside the input file. So this is the two-way bridge connecting developers and analysts. This third method here, it is the entry point to defining your material property for any material object. So this method is called at every element. So what the MOOS framework does for us is whenever we create a material object, well, it's basically anything that derives from the base class material, it will execute it, or it will run it at every element during the element loop. So in other words, when we are looping through the elements, this method is called for each and every material object. Okay, and we have a default implementation for compute properties, which is simply looping over all the quadrature points, and then at each quadrature point we call this method compute QP properties. Well, so that's so for example, for standard materials without any stabilization, that's all you need. This is the only method you need to override, right? So you just need to define what your material properties are at each and every quadrature point. But for this tutorial, though, for this example, since we are implementing the three-field formulation, which is a form of stabilization, we will need to compute some quantities, remember, we need to compute P and theta, which is element averaged quantities. And so we need to override this compute properties method as well. Okay. And then everything else will be related to our custom material. So I have provided two helper functions. Well, these two are the penalty functions for incompressibility. So remember, in the formulation, that's basically H as a function of J. and h takes the form of j to the power of beta plus j to the power of minus beta. So basically beta is a parameter controlling the compressibility of the material. The larger beta is, the more incompressible the material is. So that's how we interpret this function. So that's implemented for you. So h is the penalty function, and dh is the derivative of h with respect to j. We need that function in the definition of the hydrostatic stress. So naturally, when we take derivative with respect to the Cauchy-Green strain, this term shows up. And this is the isochoric stress. Well, so again, I want to reiterate to make it absolutely clear. The only necessary methods for you to override in the material class is this compute QP properties. This is the method that has to be overridden. Okay, and everything else is optional, so that you can have as many functions as you want to make your code modular, cleaner, and easier to read. That's completely up to you. So in principle, I can squeeze everything into one single function, but that's not good for maintainability and readability. So that's why I'm creating all these helper methods. So this isochoric stress takes in the Jacobian and the right Cauchy-Green strain and returns the isochoric part of the second Piola-Kirchhoff stress. So this method I've implemented for you as well. And then for these additional members of this class, we have deformation gradient for sure. That's what we need to compute the right Cauchy-Green strain. 3 material properties. So that's K as bulk modulus, mu1, mu2 as the ad hoc shear modulus. Beta is the parameter. Remember, beta is the parameter controlling the compressibility of the material. And then I have 3 additional members: theta, lowercase p, and uppercase p. So there's a subtle difference. Well, so if you're careful with this, you may be asking why, for example, the deformation gradient is a AD material property and it's a constant reference, but for theta p and capital P, they are not constant reference, right? So the way to interpret that is, so remember in tutorial 2, we made our material modular by creating a strain calculator and a stress calculator. The strain calculator is responsible for computing things like deformation gradient and strain, and the stress calculator retrieves the strain and deformation gradient computed by the strain calculator, and then use those quantities to compute the stress. So that's so there is a dependency. There is an inherent dependency among the material objects, right? So this is in some sense indicating such dependency. So this is saying this material we're implementing will depend on these material properties. So MOOS will make sure that the material objects that compute these properties will be executed before this object. So at the time we're inside the compute method of this material, all of these properties will be available. They have already been computed by someone else, right? And so we make sure these are constant references. And I don't know if you remember the C++ syntax. When you mark something that's constant, you basically cannot modify it. That's the easiest way to understand what's going on, right? And then these properties are not marked as constant, meaning that in this material we will be defining what they are, right? So that's the way to interpret this const mark here. And here is a hidden method which is the one I want to implement. So that is the volumetric part of the stress. I will call it volumetric stress. It will be a function of, let's see, it will be a function of the Jacobian as well as the right Cauchy-Green string. And then you may be wondering, well, so let me hide this one. You may ask what this const here means, right? So I just went over the const decorator here. So they mark these members as read-only, basically. And then when you mark a method as const, essentially this is saying this method will not modify any of the members of this class. This is just some way to well, this is considered the best practice for C++ development. It provides the compiler some hint to optimize your code to make it run faster, and it also prevents, for example, in the future, if someone wants to derive from your object, you are essentially enforcing that whatever you do will not modify any of the data structure I maintain locally. So that's what this const decorator here does. Okay, so now, so that's everything inside the header file. Any questions so far? Hopefully this is, hopefully I explained it here.
No question.
Oh,
okay. I mean, Gary mentioned there are two properties, right? One is that those two know the dependence. Second one is you don't want user to change them. But also, you remember, if you remove that constant, the compiler, you cannot compile the code because the function to fetch the material market is constant. So you have to make that property as constant in order to compile to able to compile.
Yeah, that's a good point. So for those of you online, so when I was making a point that if you remove these const decorators, your code won't compile. That's yeah, that's one way to that's an additional consideration. Yeah. So I assume everyone has your code editor working and your header file completed. And so let's move on to the source file.
Oh, one quick question from the online auditor. So the yesterday you mentioned that you will say a couple words about this AD thing. So yeah, maybe you can explain what AD means.
Yes. Thanks for the reminder. So let me think about where to start. So let me write some pseudocode here for the purpose of explanation. So let's say when you have a so in C++, the double precision type is double, right? So you have double A equal to 1.0. That assigns A with value 1.0, right? And for in Moose, we have a type alias for double precision floating point numbers, which is real. So this is equivalent to this is equivalent to A is equal to 1.0, and it's A is of type real. Okay, so when you evaluate a function, for example, you can have a function which is my function as a function of A, and it returns I don't know, maybe std sign of A. It returns the sign of A, and you say, well, let me make it X and Y for the purpose of understanding. and y is equal to my function x, right? So y will be some real number as well. So this is called non-AD. Well, so let me make a comment here. This is non-AD, right? And then if you want to, so in many scenarios, in finite element simulations, you need to compute the derivative of your functions. For example, the derivative of your strain with respect to, the derivative of your stress with respect to strain, that gets assembled into the matrix, the big matrix. Some people call it the Jacobian, some people call it the tangent stiffness. I think it depends on your background. Anyways, so that's necessary, and so what we will have to do is write another function called my function derivative of x. So that's basically return std cosine of x, right? And so we will have to do dy dx equal to my function derivative and pass it to x. So this is the non-AD way of doing things. And so in MOOS, in order to do this, you need to say, so instead of, so yeah, I mean, the conversions is very simple. Just remove all the AD prefix here. You will get a non-AD material. And because you're not using automatic differentiation, it is your responsibility to tell MOOS what the derivative of stress with respect to strain is. You need to derive that on your own, and you need to compute that inside your compute QP properties method, basically. So that's the non-AD way of doing things. And then for this workshop yesterday, everything we wrote in tutorial 1, 2 were using AD, right? So let me explain what AD is. So let's consider the same function here. We have a so now instead of a real number, we use an AD real x is equal to 1.0, and then the function now will be changed accordingly. So as you can see, the implementation of the function itself is largely the same. The only difference is in its return type, right? So and when you evaluate the function to get y, you do AD real y equal to my function x. Okay, so so far, the AD version is almost exactly the same as the non-AD version. And what this new data type here means is it creates an additional set of the so-called dual numbers for us to keep track of the derivatives of your function evaluation. And if you're interested in how dual numbers work, I think there's a very nice Wikipedia page. Well, let me show that anyways. There's a very nice Wikipedia page if you just search for dual numbers. The first page that pops up is the Wikipedia page explaining what dual numbers are. It's basically a technique to help us automatically keep track what the derivatives of a function evaluation is. Okay, so since we are relying on forward mode automatic differentiation using dual numbers, this is all you need in order to evaluate function and the derivatives. And then the derivative dy dx can be just extracted from your so those dual numbers will be your derivatives basically. And so we have some method called, I don't know, extract derivatives. By the way, these are just pseudocode for me to explain what AD is. extract derivatives. So that's all you need. So as you can see, it removes the overhead from developers and users for deriving and defining derivatives. So all you need to do is to implement your material model, your kernel correctly, and your and a mousse is responsible for extracting the derivatives out of the function evaluation automatically, and you don't need, for example, you no longer need to define the derivative of stress with respect to strain inside this compute QP properties method. And then so here I'm focusing on the material model, but the same rule applies to kernels as well. So so just to recap, kernel is basically the terms representing the is basically representing the terms in your weak form, right? So now you only need to define the residue of the kernels and for each kernel, and you don't need to define the derivative of residue with respect to the degrees of freedoms in your kernels. That's also done for you using automatic differentiation. So I think that's a long way of explaining what AD is, but hopefully that answers your question. So that's the difference between AD and non-AD. So AD is more convenient, and there are some other advantages.
No, thank you. That was very nice, actually, and I think it's very important part of the basically understanding how they if you involved in actual code development, so to understand that what it means.
So I think now I can comment on some pros and cons with AD and non-AD. So
okay,
So if you're so if AD is so nice, right? So people will wonder, why don't we completely get rid of the non-AD version of mousse, right? So that's a valid question. So AD is very useful in terms of rapid prototyping, and it is very useful when you do multiphysics coupling, because I'm sure if you have done that before, deriving the derivatives or the Jacobians for the off-diagonal terms of your multiphysics coupling is a pain. It's very painful. And so if you use AD, you no longer need to worry about that anymore. So it's very convenient, and it allows you to do rapid prototyping. However, everything comes at a cost, right? So if you use AD, though, there is a performance penalty. So we have done some profiling on some of the existing code. So for example, for the Navier-Stokes module for fluid dynamics, they are entirely relying on AD because they have done the relevant profiling. They've demonstrated that if you use AD, the performance penalty will be about 10%, right? So if your code takes 100 seconds to run, and now if you use AD, it'll take probably 110 seconds. That's the performance penalty you need to withstand if you use AD. And I do want to comment that such overhead or such performance penalty depends on your problem, depends on your material model, depends on the problem dimension. And I think it would be a good practice to try to implement your prototype in AD first, and then see if there's any hotspot in your code, and if so, try to change it to the non-AD version and see if that can speed up your simulation. Okay, so for a production build, when you actually want to package your software, your application, and send it to other people for production purposes. So that's the pros and cons of AD and non-AD.
Thank you. One quick question. So it is clear why the AD is added to the function, but then what would be the benefit of calling a scalar with AD?
Calling a scalar.
Yeah, like a AD real x equal 1, right? So what would be the why do we need to do that?
Yeah, so the internal data structure of an AD real is basically, well, so here's pseudocode again. For example, the internal data structure of an AD real looks something like this. So the value and let's say some container, maybe an STD vector of, well, let's say STD array of real 50. So this is the internal data structure of AD real. So when you set 1 to an AD real, it basically assigns the value to AD real, and then we do need to keep all these dual numbers in order for all the derivative information to propagate. I think that will become clear if you read through that Wikipedia page. I think you can even find some prototyping implementation of AD online for the purpose of understanding.
Okay. Yeah. Thank you. I think it's not a matter of this workshop anyway. So yeah. But thank you. Yes.
Yeah. Okay. Yes.
I just want to add a.
Oh, I will hold on. Let me mute myself.
Yeah. So since we're talking about AD now, I think it's a. I just want to add 2 more things. I think it's good. So Gary mentioned about the performance, right? But as we know, when we evaluate the AD type data, we carry out derivatives. That's a dual number every time we calculate. So that's extra cost of computing. But I think one thing that AD can outperform non-AD or some hand-coded thing is it provides perfect Jacobi. And once everybody here probably know, once we have a good Jacobian or perfect Jacobian, we got quadratic convergence rate. So that means you can use much less number of non-linear iterations. That effectively, maybe we lose some computation where we have actual computing for those materials at each quadrat point. However, we save a lot of computing in non-linear iterations. Think about if we cannot provide a perfect Jacobian, we may end up with evaluating double number of non-iterations. So we waste a lot of time there. So I don't know that 10%. It's I think it's problem dependent. So the best practice is you try yourselves to evaluate the real performance of the AD. But everybody likes AD because it's super quick for prototype, and you don't worry about the Jacobian thing. Again, so it's a complicated thing. So you want to get the full evaluation of the AD's performance, but it's a very nice tool to use.
Thank you.
Thanks for Wen's comment. Yeah, that's a very good point, which I forgot to mention. Yeah, and then I actually have a fun story to share regarding AD. So when I was doing my PhD and when I was taking Professor Doble's nonlinear finite element course, as the course project, I was implementing some hyperelastic material as the final project. And at that time, I actually cheated a little bit by using AD. So that I only have to implement the Pure-Kirchhoff stress as a function of deformation gradient, and I was able to get perfect convergence with the with AD because the Jacobian is perfect. And implementing such derivative is not a trivial task. So after I implemented the AD version, I tried to switch back to the non-AD version by manually deriving the Jacobian. It took me a fair amount of time to get that to work. So that's something to consider as well. And indeed, when the Jacobian is not perfect, it took way more nonlinear iterations for the model to converge.
If I can just comment to the students, we won't be insisting that theory trend. The other thing I'll say is that debugging by-hand Jacobian can be really a pain, because essentially almost one way to debug is effectively apply a finite difference. Okay, considering the function at some deformation and then some deformation plus an epsilon, and dividing by epsilon and trying to see how the values you get for that finite difference compare to what your actual Jacobian value are. So you do that one at a time, but it's really pretty labor intensive to debug by hand. So obviously, one way of saying I agree with Glenn. I think in the end, the performance hit that you take is minuscule compared to flexibility and accuracy.
Okay, it seems like everyone is embracing new technology now. Okay, so now let's move on to the source file. Oh, by the way, can everyone hear me still? Let me make sure I'm yeah. Okay. I assume everyone can hear me. Anyways.
Yes.
Okay, thank you for confirming. And then, so now we're ready to look at the source file now. The very first thing to do is to include your header file. I often forget to do this on myself. Just don't forget about this. Otherwise, you'll get a lot of compile errors. And following the first include, that's other additional header files you want to include, which provides additional functions or data structures you want to use for this object. And here I've included this helper header here for me. Well, later on we will see this helper function for us to compute element average. And as we've seen yesterday, every object has to be registered. Well, so every usable object has to be registered using this function call, using this macro here. So what this does is it's telling Moose that this object can be created from within the input file. That's basically what it says. And if you are developing several different applications, this first argument will be the application where you want to register this object to. Right. So for example, if you register this to Snail app, to our Snail app, then you won't be able to find this object if you're using the solid mechanics executable or some other applications executable. You won't be able to find this object. You can only find this object inside the Snail app using the snail-opt executable. And then this is the implementation of the valid params method. Remember that this is the entry point for us to tell Moose what to expect from the input file, right? So, so first of all, we should retrieve the parameters, the parameters that have been already registered in the base class. So we retrieve that by calling the base class valid params method. And for documentation purposes, it is always recommended to add it can be very simple. Just add a one-liner of class description. It really helps your users, trust me. Otherwise, they will come to you and ask, what is this? What does this object do? And then you will have to spend more time explaining what what's the functionality of this object. And you can, in fact, I think, put LaTeX formulas here. So, for example, you can, I think the syntax is y equal to x or something, some LaTeX formula here, or I think you can even put LaTeX symbol here, but you need to do double escape for the string parser to parse it properly. Anyways, so that's the class description. And recall that we want to retrieve the deformation gradient computed by the string calculator. So we need to add a parameter, which is of type material property name here. So the first argument is the argument is the name of the parameter that shows up in the input file. So the input file, if you will in order to change the default parameter name of deformation gradient, you will say deformation underscore gradient equals some other name. That's what this first argument means. The second argument means the default name of this material property. So for example, your string calculator may declare a material property for deformation gradient, but they may be calling it def grad, maybe calling it FM for whatever reason. So this provides the flexibility if people want to reuse your object, but their string calculator declares the deformation gradient using a different name. But the default here is F, so meaning that I'm expecting that, by default, the deformation gradient is declared as F. And the third argument is again, the brief documentation of what this parameter does. And later on in tutorial 13, I will show you how to automatically generate all the necessary documentation for your application. For example, for this snail app, you will see that it automatically extracts all this class description, parameter description, and put it into a nicely formatted website so that you can host it on some web hosting services. So that's what this function add param does. And then you can see some variants called add required param. So what this does is it's very similar to add param, but instead it's well, as its name suggests, it is a required parameter. So the user must define this inside the input file. And so this method only expects two arguments: the name that shows up in the input file and the description. It doesn't provide a default because, again, it is required, right? And similarly, the shear modulus 1, shear modulus 2, that's mu1, mu2, and beta is a parameter controlling incompressibility. I have two additional material property names here for me to hold the element-wise constant auxiliary field. That's the element dilation and hydrostatic stress. Okay, so this defines, again, let me reiterate, this defines what will show up inside the input file. And then this constructor is what we use to construct this object from the parameters extracted from the input file. All right, so first of all, we construct the base class material, because remember, we're deriving from the base class material. And then this is how we initialize the members. So if you are retrieving a material property, you use the get material property function call or get AD material property function call. And the template argument here denotes the type of the data. So for example, this is a rank 2 tensor, and for K and mu1, mu2, these are real numbers. And for a param where, so for example, this beta, this is not considered a material property. I'm considering it as a just a parameter, meaning that it's a parameter inherent to this material model, and you won't see spatial variation in this parameter, and so this is how to declare such parameters. And in order to retrieve that parameter from the input file, just to get param templated on the type of the data. And so these are the function calls to initialize material properties that are retrieved from other materials. So in this case, the string calculator will provide the deformation gradient. And in the input file, we will define other materials to define these material properties, K, mu1, mu2. And beta will be just a single number. And then in order to declare new material properties, well, so these properties are what we will define inside this material object itself. We use the API called declare property, or declare AD property, templated on the type of the data. Okay, and yeah, I think that's all I want to talk about for the validate params function and the constructor. And now, so okay, so here are the implementations of the helper methods H and DH. Remember, these are the H is the penalty function, and DH is this derivative with respect to the Jacobian. So now this compute properties method is what we need to implement, as well as the compute QP properties. Well, so let me first implement this compute QP properties, and then we will go back to the compute properties method. So compute QP properties, we will be, well, so let's first go back to the definition of the second Piola-Kirchhoff stress. It's equal to the sum of the volumetric stress plus the isochoric stress. And this is the definition of the volumetric stress. It's P, which is the hydrostatic stress, times J times the inverse of the right Cauchy grain strain. And then, well, so let's just faithfully implement that in our source code. So, first thing to do is to
excuse me, I have one question.
Yes, please.
Please, what's the difference between declare AD property and get AD material property?
Yeah, so declare yes, for declare property, you are basically declaring these properties so that Moose knows that in this material object you will be computing the values for this material property at every quadrature point. So it serves as two purposes. First of all, it initializes this data member for you. So that's the first purpose. The second purpose is so that Moose knows that this material is the provider of this material property, so that later on, if you create some other material objects that wants to retrieve this material property, Moose knows that well, so this tutorial 10 stress will have to be executed prior to.
Oh, I got it now.
Okay, and then
thank you.
Yes. Well, just to make it complete, for get material property is the other way around. You are now retrieving the material property from someone else, from some other material object, and in those material objects, they must be declaring these corresponding material properties. That's the difference between get and declare. Okay, so now let's.
Thank you.
Okay, you're welcome. So let's move on to compute QP properties. So first of all, let's assume that well, so it's compute properties responsibility to do stabilization for us. So here, let's assume the element average properties are already available. But first of all, we need to first compute the element the Jacobian at the current quadrature point, which is J is equal to the determinant of the deformation gradient, right? So underscore F is the, remember, it is the deformation gradient material property, right? And because we have more than one quadrature points per element in general, we need to index it using the ID for the current quadrature point. So if you have a, if you use first order quadrature rule for first order Gauss quadrature for Q4 element, you will have 4 quadrature points. So underscore QP will be taking values from 0 to 3. So 0, 1, 2, 3, right? And then this should give us a rank 2 tensor or AD rank 2 tensor. And then the Jacobian is simply the determinant of the deformation gradient. So we call the determinant DET method on that. The return value is going to be, sorry, it's going to be an AD real because this is an AD rank 2 tensor. And then I recommend, because MOOS is now using, has adopted C++17 now, and we have pretty good support for C++17, and so we can just use auto here. If you, this is first of all, this is error. This is it's very difficult for you to introduce any mistake here because it's automatically deduced by the compiler if you say auto, and it also allows for some potential compiler optimization here. So I would recommend you to use auto wherever possible. Okay, and then I was expecting a question here. I was expecting someone to ask me where to look for all these APIs. So this DET method, along with a lot of other methods here, their documentation is available on the MOOS official website. And let me show you where that is. So for developers, you can go to documentation, framework development. There's this documentation section with MOOS oxygen, modules oxygen, lead mesh oxygen, TIM, PI oxygen, and many other oxygen documentation. So for this one, we will be using the MOOS oxygen. You can search for rank 2. Well, so in this case, we're looking at AD rank 2 tensor. Okay, I found it here. So now you can see AD rank 2 tensor is just a type def of rank 2 tensor templated on AD real. So the real documentation will be here in rank 2 tensor template. And now you can browse for all the available APIs that are exposed to you. So for example, in this case, the API we're going to use is DET. It returns the determinant of the tensor. Yeah, and then there's a brief summary of the implementation and some additional documentation. And also where this method is being used, you can click on that to see if you want to look at some examples using this method. So that's where you can find all those APIs. Yes.
Also, you know, the rules that you write from lead mesh, and some of the useful functions of lead mesh can be found on the blockchain, the lead mesh blockchain website.
You are correct, but that's no longer necessary. Let me show you. Well, so Wen was mentioning that because we have so many systems in MOOS, we have MOOS, lead mesh, and etc. You may need to go through different oxygen documentation in order to find what you want. But I was answering him that that's no longer necessary here because now we are integrating all the oxygen documentation in one place. Let me go to the rank 2 tensor. Where is it? Here. So for example, you can see that some of the method here, well, it's probably difficult for you to see from the projector here. Some of the method is bold blue, like these constructors, this method column, operator equal, things like this. And there are some operators or methods that are light blue here, meaning that these are the methods inherited from the other documentation side. For example, these are methods provided by LibMesh. But anyways, my point is it's no longer necessary for you to navigate through different documentation website. We've put everything in the same place. Okay, let's continue. So this is the first line. This is how we compute the Jacobian, and with also we need the right Cauchy-Green strain as the argument to the volumetric stress and isochoric stress. So R2 const R2 C is equal to FQP transpose times FQP. So this is the definition of the right Cauchy-Green strain. And with that, we can just call this isochoric stress method, which I have already implemented for you, to compute the isochoric stress. So that is const R2 SI isochoric equal to isochoric stress. The function requires two arguments, J and C, which we already computed. So that's J and C. Okay, so now we've computed the isochoric part of the second Piola-Kirchhoff stress. So now we need to implement the volumetric stress. So I think this is where I put the implementation of the volumetric stress. It'll be AD rank 2 tensor volumetric stress with the same function signature as isochoric stress. So that's AD real J. AD rank 2 tensor C. The volumetric stress, the definition, well, let's, as a reminder, the definition of volumetric stress is P times J times the inverse of C. Easy enough. So just return P times J times the inverse of C. Okay, that's it. That's volumetric stress. So now in the compute QP properties method, we can use this helper method to compute the volumetric stress, which is like this. Everyone following so far? Okay. So now we have both isochoric stress and volumetric stress. We can compute the first Piola-Kirchhoff stress now. Well, remember, because the kernel we've implemented just does the, it's the divergence of stress. And I didn't specify whether that's Cauchy stress or first Piola-Kirchhoff stress on purpose, because then we can reuse the kernel for large deformation as well. So it's a divergence of the first Piola-Kirchhoff stress. And so for that, in that case, I need to define the stress using the first Piola-Kirchhoff stress as the stress measure instead of second Piola-Kirchhoff stress. So I need to do an additional conversion here from PK2 to PK1. Okay, so the expression inside the braces here is the second Piola-Kirchhoff stress. It is the sum of the volumetric PK2 plus isochoric PK2. And then the relation between PK2 and PK1 is PK1 is equal to F times PK2. That's it. Okay, so that's all we need for the compute QP properties method. But there is still something missing, which is the stabilization. So remember the volumetric stress. We defined it as the hydrostatic stress times J times C inverse, but we haven't computed the hydrostatic stress yet. So we need to do that in the compute properties method. Why can't we do that inside compute QP properties method? Because we need to loop over all the quadrat points in order to compute the element average of the hydrostatic stress for stabilization purposes for using the three-field formulation. Okay, so now let's implement the compute QP compute properties method. So the very first step, if we look at equations, is to compute the element average of the Jacobian. So to do that, let's first initialize a theta average. Well, let's do theta sum equal to 0. And we also need element volume. So that's element volume. And then we need to loop through all the quadrat points to sum up the element Jacobian as well as the element volume. So for unsigned, well, so it's for QP equal to 0, QP less than Q rule and points. Yes, David.
What's the difference when QP properties is called versus QP properties?
Yeah, that's a good question. So David was asking, what's the difference between compute properties and compute QP properties? The answer is, well, first let me comment this out. The answer is, compute properties is the public method that will be called by others. So other objects will only call, well, for example, Moose will only call compute properties method. Other objects will not call compute QP properties method. The way to understand the relationship between them is for prototyping, right? So you can think of it as this. So it's essentially looping through all the quadrat points, and at every quadrat point, it calls the compute QP properties method. So this is the base implementation of the compute properties method.
So they're both on the curve.
They're both so. Well, I would say all the material properties should be calculated at the quadrat points. These are just two levels of function calls to make it more modular, because for a regular material, you don't, I mean, we don't want to let the user to manually loop through all the quadrat points. That's additional effort, I guess. So as the user, as the developer of your application, most often you just need to override this compute QP properties method. But in cases like what we are doing here, we need to compute some additional element average, which requires an additional looping through the quadrat points, and that's where we need to override the default behavior compute properties. So this is where we will compute P and the theta averaged over the entire element. Yes, correct. So for regular, well, this is probably not a very good tutorial example now. For regular material, you just need to override compute QP properties. That's evaluating, well, there's zero non-local information among quadrature points, right? You just do what you need to do at each and every quadrature point.
So you're right. I think there's a lot of loose your system. You just need to properties. But also, this is for computers object. I believe is the machine other objects as well. Those processor, other cases, you might end up with considering this different functions as well. So for this processor, you might also have to override the properties as well. Because it will give us advantage for do some special things. It was all part of these things. So I have another question. Can we scroll back? Yeah, what is the using transfer indices? What does that mean?
Oh, so for those of you online, when was asking what does this using tensor indices IGKL means? This is a new capability to support some of the Einstein summation conventions. It's so for example here, this is delta IK times delta JL basically expressed using the Einstein summation. We don't want to maintain so many different copies of the method. So imagine I think in MOOS we used to have like mixed product, IKJL, things like this. We no longer need to use those. This is the new way of doing Einstein summation.
So automatic, so it just knows that that's, like you said, it knows it's Einstein summation.
Yes, so this is equivalent to just unrolling it to for I equal to 1 to 3, for K equal to 0 to 3, something like that, and it performs Einstein summation for you. Okay. So let's go back to computing the volume average of element Jacobian now. So at every quadrature point, we just use the quadrature rule, which is theta sum plus equal, what is it? Let me check. It's the determinant of f, which is the Jacobian for that quadrature point, times jxw. So this is the W is the weight of Gauss quadrature, and J is the mapping between parametric coordinates and the current element coordinates. So this is this is finite element basics times chords QP, where this final factor accounts for different coordinate systems. This is how you do element-wise quadrature to compute the sum, to do element integral, basically. And the same thing goes to element volume. Okay, so this is I'm writing it this way for you to understand what's going on behind the scenes, but you don't have to do this in practice, because remember I included this stabilization utils helper method here. So this routine can be replaced by the stabilization utils like this. We can directly compute the element average of theta by calling stabilization utils element average. So this function takes several arguments. The first argument is a lambda function that returns the value for each and every quadrature point. So I'll just write it down and then explain. The second argument is the JXW factor. The third argument is the chord factor. Okay, So this is how you compute the element average quantity. So the first argument is a lambda function, which basically tells this helper method how to get the property that you want to average at every quadrature point. So what it does behind the scenes is this. So there's nothing special about it. It's just a convenient helper method. So this is how we compute the average of the element dilation. So once we have the average, I think I have an additional function call here, theta set all values theta average. So this is because I want to assign the same value to every quadrature point for convenience, so that later on we can just use QP to access this averaged quantity, and for visualization purposes, it's easier to directly output this as a material property. Yes.
Why does the stabilization details require you to pass JX? Why doesn't it just use that Jacobian time stability?
Why does it what?
Why do you think that? I'm surprised you need to pass in.
The JXW?
Yeah.
Because when you use Gauss quadrature, you need to use the JXW to do Gauss quadrature, I think.
Right. I'm surprised it's not part of. It's not underneath in this element average routine. So.
Yeah, I mean, yeah, okay. So the element average routine doesn't know which object is calling it, right? So different object may be using different quadrature rules, right? So I'm basically passing this material object's quadrature rule to the helper routine so that it knows how to do integration. Okay, so this is how we get the element average dilation, and we do the same thing to compute the element average hydrostatic stress now. P average equal to element average QP. So the expression here will be the bulk modulus times dH evaluated using the averaged dilation, and that's it. Also pass it with the JXW and coord. Oh, by the way, it should be coord here. And same thing, we want to set its value to all the quadrature points. So lowercase p, set all values p average. And that's it. That's how we do the three-field formulation. Basically, it's fairly straightforward once you understand the math and knows how to compute the element average. So at the very end, we should also call the base class, which in this case is the material objects compute properties method. So what this does is now, after I've computed all the average values for using the three-field formulation, now it's time for me to compute the properties at each and every quadrature point. Now this method will loop through all the quadrature points and then call the compute QP properties. And when we are evaluating the volumetric stress, this hydrostatic stress will already be available to us because we've already computed it here. Okay. So that's all we need for. Sorry, what? Oh yes, you mean this ampersand? Yeah. So let me think. Well, by the way, this is to capture this is for the lambda function to capture everything within this scope. Well, let me think how to explain this. So for example, if you remove this ampersand sign here, what this lambda function captures is this, which is this object itself. It will only have access to its members, which is underscore k, and this member function dh here. It will not capture this theta average, because theta average is not anything that belongs to this. It only exists in the local scope here, right? So this ampersand sign here is telling this lambda function to capture anything within the current scope, basically. Well, that's advanced C++ usage. Okay, so that's
Is that a function?
yeah, this is a function implemented in this namespace. Yes, the lambda function you create that on the fly. Yes. This namespace is for the element average method. This method itself is not the yeah. So the lambda function is here. Okay. I mean, I totally understand this is considered to be modern C++. I mean, it took me quite a while to understand all of this, and there's nothing wrong with unrolling this to to write your own for loop and something like that. There will be negligible performance difference. They should be identical in principle. So there's well, my point is there's nothing wrong with for loop. If you write everything using for loop, it ought to work. That's the beauty of C++. Okay, so that's everything I need to implement this three-field formulation, hyperelastic material. Is there anything else you want me to explain? If not, I will try to compile this, and hopefully it can compile.
Actually, yeah, would be one more question. So this regarding underscore QP, this is basically somehow kind of like globally declared variable that is available to the everywhere.
Yes. Let me show you. Let me show you the source code of the base class. You can, by the way, you can always do this on your own. You can check what the source code does, because Moose is fully open source, right? So you can always do this. So let's go to the material class. Where is QP? QP is probably not here, then must be in material base, I guess. By the way, a better way of figuring this out is by looking at the Doxygen documentation. Well, okay, so QP is defined here. There's nothing special about it. It's an unsigned int underscore QP. When we call the compute QP, when we are inside the compute properties method, we loop through this. We increment its value from 0 to 1 to 3 to 4 to all the Cauchy point IDs. In fact, let me check if there's a compute properties method here. Yeah, so this is the prototype code I've shown you before. Wait, hold on. Yeah, this is the prototype code I've shown you before. It basically loops through the each and every quadrant point and calls the compute QP properties method.
Mhm.
All right.
Okay.
Okay, it compiled successfully, and now let me run the. So we should go to tutorials. I think it's 10, and let me check if I need to modify the input file. So for the input file, I've provided you a mesh, which is basically a piece of paper with a meshed in crack in it. So we're reusing the two kernels we implemented in tutorial number 2, but now the stress name is called PK1 stress. That's what's defined by our custom material object. And here is the place for us to define our stress model. Oh, and by the way, I think I talked about this yesterday. There is a very nice Moose extension called, there's a very nice VS Code extension called Moose language support. And I think there is some bug in the very latest version 1.0.2 or something. So I've been sticking with the 0.7.1 version, but I'm sure Daniel will fix all the bugs in a very short time. So this is the extension that allows me to auto format my Moose input file and also auto complete the input files. So for example, when my cursor is here, if I press Control Space, it shows me all of the available objects that I can use here. And for example, if I type tutorial, it will show me the fuzzy match of the available objects. So here I will use tutorial 10 stress. I pressed enter, and this is what it looks like. And now if I press Control S to save the document, it automatically formats this block to look like this with the correct indentation. So that's what this that's part of the capability provided by this extension. So I recommend everyone using VS Code to install it. Now we, again, here, if I press Control Space, it will also tell me, it will also give me a list of input file parameters that Moose is expecting. Okay, so in this case, the ones marked as using this purple-ish cube means it's a required parameter, and the other ones are optional. So in this case, I will have to define beta, which, let me think. So here's the problem definition. I want beta is equal to 2, k equal to 4,000, mu1, mu2 equal to 3,000. So beta is equal to 2, bulk modulus equal to 4,000, shear modulus 1 equal to 3,000, shear modulus 2 equal to 3,000. And let me check if there's anything else I forgot to specify. Yeah, that's all I need. And then for the boundary condition, I'm fixing the fixing the right edge, and I'm just pulling apart, trying to tear apart this piece of paper. And then it's a traction control here, so it's a Neumann boundary condition, and I'm ramping up the force in accordance with the simulation time, and I have the simulation going from 0 to 1,000. And I'm solving this using the direct solver with automatic scaling. These are all of these we have covered yesterday. So now to run this input file, hopefully you still remember that's first we invoke the executable and then use the -i option followed by the input file path. Okay. And for this one, I want to use 16 processors. And that's it. As you can see here, we get a very nice convergence history with basically quadratic convergence. So you can see here is 10 to the -7, and the next step, next nonlinear iteration, it goes to -12s. So it's nearly quadratic, I would say, and we go and it goes down. It goes down to machine precision. So this is the benefit of using AD, because our Jacobian is guaranteed to be exact. If you are using some hand-coded Jacobian, and if you happen to make some mistakes in the derivation or implementation, your convergence history may not be perfect, and you may be, as Wen pointed out, you may have to take more nonlinear iterations. And to visualize the result, well, okay, so there's one thing I forgot indeed. So in the input file, so now let's say I want to visualize the element averaged hydrostatic stress and element dilation. The way to do that, so there are several ways of doing that. One shortcut for that is to say there are some properties I want to output. That's this output properties option. You can say, let me see, what's the name of the property? It's called theta and p. So it's theta and p. And I want to output it to Exodus. So this will automatically create the auxiliary variables and auxiliary kernels necessary to extract these material properties and project them onto the corresponding aux variables. So now I have to rerun this, unfortunately. And we can use Parallel to visualize the result. So this is the original geometry, and you can see there's a tiny meshed in crack here. And so when I try to pull the paper apart, it should form like this. And if I want to look at the pressure field, for example, this is what it looks like. So it's in tension near the crack tip, and it's in compression near the middle of the top and bottom boundaries. And if you look at the element dilation, it's above 1 near the crack tip and smaller than 1 in the corresponding compressed regions. Yeah, so well, you can make the picture fancier by choosing your favorite color map for sure. But this is what it should look like to make sure everyone can get to this part. Because later on in tutorial 11, we will be implementing the phase field fracture method based on this new Hookean material.
Gary, I have just a question. So basically, to run the tutorial, I have to run it parallel with the Moose, right?
you can run it in serial. So let me show you. So you can always run it in serial. That is, you can either say MPI EXEC-N1, that's in serial, or you can just remove this. So that's just invoking a program in serial, and let me show you. It's noticeably slower, I would say, but it's okay if that's all the computing resource you have.
Yeah, I was following you exactly with the same steps, but my solution for some reason didn't converge.
Okay.
Mine too.
Let me think. Can you maybe show us? Well, I mean, this is a very good debugging tutorial, I guess. Can you show us the convergence history? When you are saying it doesn't converge, can you show us what's printed to the console, and then we can look at it together?
Basically, what it shows, I had an error as well. So it occurred in the object constant dt.
Can you maybe copy paste your screen output somewhere so that all
Sure.
of us can look at it? Yeah. Or maybe Pawan, you can show us your screen output as well. But we can look at either one.
I just posted it on Slack.
Oh, Slack. Okay. Okay, so let's look at the first one. Yeah, this is most likely. Yeah, I think Bo is right. If you look at your source code, here after we've computed the element averaged theta and p, we need to call the base class compute properties. Otherwise this first Piola-Kirchhoff stress will stay 0. That's very likely what's going on, because here all you are seeing is a residue that's equal to 0, which would suggest that the stress you computed is very close to 0, I would say. So that could be the reason.
Actually, I called it. It's in the. I do have it as well.
Gary, the exact codes are in your repository, right? So they can just copy them.
Yeah. So yes, I mean your sort of last resort would be copying from my snail repository and use those and see if that can converge. But if still that cannot converge, that's for sure a bug, and we need to look into that. But I doubt that's the case, though.
Honestly, I did the same thing. I got, because I was following you. I did, my solution didn't converge, and then I copied it from same thing.
Really, that's very.
But that's fine. We can look into it afterwards.
Yeah, I believe it should work, though. Yeah, so maybe let's look at this after the the workshop, I can help you debug.
Okay.
And for powers, so this would suggest that you are not computing the Jacobian correctly, because so first of all, the linear solve cannot factorize your preconditioner. So are you sure you're using AD?
Yes.
So for me, the 0th iteration residue is 2.19 times 10 to the minus 5. And for you, you are seeing a very different nonlinear residue as well. And so I would double check in your code to see if you have the correct definition of the first Piola-Kirchhoff stress.
Okay, let me check.
I have a problem here too. I have an error message saying that the tutorial 02 kernel is not a registered object. So I'm wondering if this depends on tutorial 2.
Oh yeah. Okay. So are you for those of you who are having trouble? So that's a very good point. Because we are relying on we are reusing the kernel from tutorial 2. Make sure you are using the correct implementation for tutorial 02 kernel as well. So if you don't have that, then I'm sure you will see things like that. So in tutorial 2 kernel, so if you open tutorial 02 kernel, you should have this compute QP residue method defined here. Otherwise, I think that's exactly what you will see in your output.
Yeah, thank you.
Yeah, though so that's not, so that comment applies to both Abhishek's result and the Abdulmohsen's
Actually, I have the tutorial right as well. Like I checked it, kernel tutorial 2.
Do you remember to recompile your snail? Like
Yeah,
after you
I compiled it.
Huh. Then that's really weird. Yeah, that's what. Yeah, but he's suggesting that he implemented that kernel. So yeah, maybe let's try to do an offline debugging session, I guess. But I do want to make sure for the rest of you, everything is working fine.
Yes, it worked fine for me.
Okay, great. Oh, then, by the way, this may be a very naive suggestion, but when you modify your source code in the editor, make sure you save them before you recompile. Otherwise, I don't think it will take effect. In fact, we ran into something like that yesterday. So just to make sure your source code is up to date, is your edit is in fact is taking effect. And for Pawan, I would suggest you try to copy what we have from the public snail repository and copy those answers into your own repository and recompile and see if this issue persists.
Yes, I'm checking that. Thanks.
Yeah, because what we're seeing here is a different value of nonlinear residue. So that would suggest that either your definition of the first Piola-Kirchhoff stress is incorrect, or the definition of the residue, which is defined inside tutorial 02 kernel, is incorrect. So make sure what you have is consistent with the answers in the GitHub repository.
Okay.
Okay. Now let's move on to the next example. Well, maybe let's give those folks another 5 minutes or so. Let's try to continue at 11 Eastern time.
This three-field formulation with the constant the ions that are actually stable. I think the first one is quadratic in displacement. That's the first one, like the lowest order one, you can construct where basically you have C0 displacements and a constant pressure. I think it's a quadratic. It's actually stable. I don't think the linear and displacement and constant pressure in the three-field formulation is actually stable.
You mean we need to use second order?
I think so. I think the very first element that is actually stable with a constant pressure is a quadratic element. You can do the mini element, the triangle. That mini element has basically a linear velocity plus the bubble. You know what I mean?
Yeah.
And it doesn't perform very well.
Put in your injector here, up here, and then you have server connections. So basically, you'll all the processing will be done.
Okay, I see.
It's not hard to do. It's like 3.
Anyways.
Yeah, you just have to
This is one of the reasons that I still need to figure out if I can do it, but coding the Crusoe Raviar element, because that actually is a relatively very different element. It's DG, but it's not as expensive as going to a quadratic, especially for highly nonlinear problems.
Yeah. I mean, I'm happy to implement that.
Yeah. No, I need to make sure I can do it.
Okay, great. So I see it's working for Abhishek now. Yeah, as planned. Let's wait until 11, then we will move on to the next tutorial. Oh, by the way, now that we are into debugging, let me show you my very last slide. So in order to, well, I will go over this entire slide later, but if you are having, if you believe what you're seeing is a bug, please go to here. This is the page to submit issues. So you can see we have 2,060 open issues. I mean, most of them are probably dummy issues for us to keep track of everything. So the real bugs the number of real bugs is much smaller than 2,000, trust me. But so this is the place to go to if you believe what you're seeing is a bug. When you open an issue here, make sure you include a minimal reproducing example so that it's easier for other people to reproduce and help you debug. The other, so similarly, if you have a feature request, for example, if what you're asking does not exist yet in MOOS, and you believe it will be a useful feature, it will benefit your own research, and it will benefit the community in general, you can open a feature request at the same place as well. And we provide a template for both of them. So for example, if you choose bug report, we will ask you for a brief bug description, steps to reproduce, the impact of the bug, and an optional diagnostic output to speed up the debugging debugging process. And if you chose a feature or enhancement request, we will ask you for your motivation, design, and impact of the corresponding feature. And however, for most of the discussions where if you want to discuss your either your implementation or the theory of your of the problem that you're trying to solve, please go to this discussion forum where it's also hosted on GitHub. We have a very active discussion forum. I think I used to subscribe to this to all the updates to the discussion forum, and I receive like 200 emails every day from the from this site. So it is very active, and I will also occasionally go to the discussion forum to answer questions. So most of the MOOS developers are in fact monitoring this forum to try to help you out. So if you have questions, please do not hesitate to open a new thread here. And usually I think there will be someone getting back to you within a day or so. A lot of times it will be faster than that. Okay. It's 11:01 now. If you are still running into convergence issues for the previous tutorial, feel free to, as I said, either leave a message in the Slack workspace or open up a discussion thread in the official MOOS repository. And I'm happy to help you offline. Okay, so in this tutorial 11, we will actually be implementing the phase field fracture method. So in this tutorial, we will look at the crack propagation initiated by tearing apart the paper, this piece of paper. I do want to comment that there are a variety of ways of simulating crack propagation within the MOOS framework. I will not try to comment on the which method is the best here. I think every method here has their usage scenario. So we have the cohesive zone method in the native solid mechanics module. We have some local damage models. Also in the solid mechanics module, as well as in the Black Bear application. So this is an public application developed by the Idaho National Lab. It has a gallery of degradation models for concrete and the similar materials. And we also have the XFAM module as the extended finite element method. This module is primarily developed by Ben Spencer, who was here yesterday, and Dr. Wen Jiang, who's here in person. And last but not the least, we have the phase field fracture method. I know many of you think of it as a gradient damage model. So this phase field fracture method is what we're going to implement in this tutorial, and there is a public application called Raccoon, which offers many of the basic capabilities for phase field fracture simulations. Okay, and there's an additional comment at the very bottom. So coupling. So here I'm showing the coupling between displacements and the phase field representing the regularized cracked surface, basically. But the coupling with other types of physics or other types of equations can be done in pretty much the same way, right? So I will so in this tutorial, you will learn how to write new kernels for coupled physics, as well as how to retrieve coupled variables from your material object. So these strategies, these routines is applicable if you want to develop your own set of multiphysics coupling with solid mechanics. So a very brief review of the theory in case you are not very familiar with phase field fracture. So recall that we showed, so let me make it full screen. So recall that we defined the string energy density function for the solid in the previous tutorial. So now for phase field fracture, we need to add in an additional contribution for representing the crack surface energy. And so the total energy can be expressed as this psi equal to W plus this additional term, which represents the crack surface energy. Where we do have to modify the string energy density function by applying some form of degradation to it. So basically, this is saying the when a solid deforms, it will drive crack propagation, and as the damage increases or as the phase field value increases, we should in turn degrade the load carrying capability of the solid material. So that's a tight two-way coupling, and this G as a function of D is the so-called degradation function. We will be using this form as the degradation function. There are in fact many other different forms of the degradation function out there in the literature. So if you take the variation with respect to the displacement and with respect to the phase field, you will recover the phase field evolution equation in addition to the balance of linear momentum equation. So for balance of linear momentum, we will be reusing what we have done already, which is basically the divergence of stress kernels. And for the phase field governing equation, we will be implementing a new kernel to solve for this phase field governing equation. Okay, so here's my plan for implementation. So this is not a trivial task, but hopefully we can get it started before the lunch break. So our plan is to tackle one challenge at a time. So the step number one, we will implement the monstrous fracture degradation function G of D. It's a complicated function, but I will show you how to implement that in MOOS in a very straightforward manner. And the second step is to modify the stress model accounting for damage degradation. So remember, the string energy density function is now degraded by the degradation function. So we need to degrade the second Piola-Kirchhoff stress accordingly, according to the current value of the damage. Step number three is to implement the string energy density as the so-called driving force for crack propagation. And step number four is to implement the weak form for fracture propagation. That's the additional governing equation for phase field fracture. So first of all, it's good news. The degradation function looks daunting at the very beginning, but it can be, in fact, directly implemented in the input file using parsed material without writing any C++ source code. So let me show you how to do that first. So I will open up the input file for tutorial 11. And I will scroll down to materials. So I'll create a new object called degradation. The type will be AD parsed material. Well, in fact, AD derivative parsed material, because we also want the derivative of the degradation function. So the first argument is the name of the material property. In this case, well, because we will evaluate the degradation function at every quadrular point. So in Moose terminology, we will call that a material property. The property name, we'll call it G. And G is a function of damage, or is a function of the phase field. So we will say coupled variables is D. But if your function, so for example, if in your own application your function has other arguments, this is also the place to include them. Hold on, let me check. And then, well, so let's review the math first. In the definition of the degradation function, we need some other constants. So namely GC, WC, and L, where GC is the surface critical energy release rate of the material. WC is the critical string energy density, where the crack will start to propagate. And L is the so-called phase field regularization length. It controls the regularity of the diffuse crack. So for L, we will define that as a constant. So that's a constant. So we have two parameters: constant names and constant expressions. So in constant names, we'll say there is a constant called L, and then constant expressions, we will say there's the corresponding expression for L is just 0.1. Okay, and we also need two additional material properties. Remember, that's GC and the WC here. So we will do material property names, GC and WC. And at the very end, that's the derivative order equal to 1, because we need the first derivative of the degradation function inside the phase field fracture governing equation. So there's one last thing that's the most important for the parsed material, which is the actual expression. So in this case, it's y minus d square divided by y minus d square plus 3/8 times GC divided by WC divided by L, then times D times 1 plus D. Okay, so this is the expression for the degradation function. So as you can see, this is essentially implementing your own object inside the input file. There is no need to write your C++ source code and recompile your application. So this provides a lot of flexibility for end users. And if you worry about the performance, I would say that for these parsed materials or derivative parsed materials, we do just-in-time compilation, meaning that when you actually run the simulation, we will take maybe a few milliseconds or few seconds to first compile the expression you put in here into machine code, and then we will compile it, and then during the simulation we will call the compiled code instead. So the performance should be fairly close to your source code. Well, there are a few exceptions apparently, but in my experience, it has worked very well. Yeah, and so that's the implementation of the degradation purely inside the input file. There's no need to write any source code. Well, I will define an additional constant here, which is eta for just in case so for example, when damage goes to 1, I don't want to completely degrade away the stiffness of the material, because that will introduce singularity in my Jacobian. I will just put a small dummy number here to prevent that, which is I think I'll use 1e minus 6. So I'll multiply the degradation function by 1 minus eta, then finally plus eta. So this just provides some residual, the so-called residual stiffness to the material. Okay, so that's step number 1. That's actually, I think I think that's actually the most complicated math of all of this. So that's already done. Yeah, I have a comment here. Parsed material and its variants are extremely powerful, especially in the context of multiphysics coupling. So in many cases, if you want to write your own application, you should probably think about whether you should actually write source code for your object, or you can just rely on the material parsing capabilities, because it's really flexible. So for in our case though, for example, for the 3-field formulation, there is no way to implement that using parsed material, at least not yet, for a few reasons. Because first of all, we are doing tensor algebra. The material, the function parser doesn't support tensor operations yet, though hopefully we'll add that in the future. And then we are, since we're using the 3-field formulation, we need to compute element average quantities, and that's not possible with parsed material. So think about it. Think about parsed material before implementing your own object. I think in a lot of scenarios, a parsed material is sufficient. Then modifying the stress is also straightforward, relying on what we've done in previous tutorials. For example, we'll just use the standard inheritance in C++ to do that, because we have implemented the stress model in tutorial 10 already. So why don't we reuse that by inheriting from what we have implemented in tutorial 10, and then just multiply the stress by the degradation function, and that's it, right? So, so let's do that now. For this tutorial, we will be editing the header file under materials. It's called tutorial 11 stress. And the source file is called tutorial 11 stress.c under the source materials folder. So if you look at the header file, we are effectively inheriting from here. So we are effectively inheriting from the stress model from tutorial 10. We're adding a decorator here, which I hope it will become clear in when we get there. So it basically adds a interface for us to elegantly define the derivative of a material with respect to some other argument. Okay. And similarly, we have the two bridging methods here. We have the valid params for defining input parameters, as well as the constructor here. For this material, we will just be modifying the compute QP properties method, because all we need to do is to degrade the second Piola-Kirchhoff stress, and as well as computing the strain energy density function. Okay, so these are the, so there's one thing I want to point out. When you inherit, when you do public inheritance, you automatically inherit all of the protected members from the base class. So remember in the base, well, let me open up tutorial 10 stress. So in the base class here, we have a few member variables, the deformation gradient, the K, mu1, mu2, beta, and etc. So these variables will be inherited here. So even though I'm not listing them here, they are available to you because we're using public inheritance. And these members here are the additional members that I need to define the degraded stress at the current quadrature point, right? So we need the phase field, the name of the phase field variable for defining the derivatives, and these two are the degradation function and its derivative with respect to damage. There are two additional material properties that we declared, which is the strain energy density and the derivative of the strain energy density function with respect to the phase field. Okay, so this variable here will be used inside the phase field evolution equation as the crack driving energy. Okay. Is there any questions so far? Otherwise, I'll start putting down. I'll start implementing the degraded stress. Yes.
Saying that it'll make sure that any modifier you use the stress from tutorial 11 will take the full derivative of whatever modifier you apply.
Not exactly. I think it will become clear when we get there. It's actually a lot simpler than what you're imagining. It's just a helper interface for us to create and manage material properties that are in fact the derivative of something else with respect to something else. I will show you that in the source code. No worries. Sorry, give me 1 second. Well, so sorry about that. So I'm looking at my answer now in my repository. I think I made a mistake, but let's see. We'll try to correct that here. Anyways, I don't think I need to override any function here, but let's see. So let's actually implement the compute QP properties method. Let's go to the source file. So first of all, we need to include the header file and then register the object to the Snail app as usual. We need to define the expected input parameters expected from the input file. the class description, well, here I'm just adding an additional sentence here. The material is degraded based on the current damage. You can elaborate on that if you would like to. So now, for coupling with another field variable, this is the API to do so. You do add required coupled var. So this will mark this coupled variable as required inside the input file. So in this case, I'm basically saying this in the input file, the user must tell me the name of the damage variable. And I'm declaring 2 additional material properties, so I need to know their names. And by default, the degradation is called G, and the strain energy density is called W. Okay. Well, there's nothing special so far. And for the derivative material interface, though, I do want to comment here. So for example, G is the degradation function, if you recall. That's what we have defined inside the input file. So we are doing get AD material property. So that's basically retrieving the degradation function computed by the AD derivative parsed material object. And so now we also need to know the derivative of the degradation function when we compute the derivative of the strain energy density function with respect to damage. So in order to retrieve that material property derivative, we use this API called get material property derivative. So this API is provided by this derivative material interface decorator. So that's answering David's earlier question. So what this material property, this derivative material interface basically provides additional APIs for us to retrieve and manipulate material derivatives. And real means the material property, material property is going to be a real number at every quarter point. True means it is AD. And then the arguments are, so the first argument is the material property. The following arguments are the derivatives we are taking with respect to. So in this case, we are taking the derivative of degradation with respect to damage. So that's what this API is doing for us. And it creates a constant reference to the material property because that's already computed by the AD derivative parsed material. And we have 2 more material properties to declare. So, well, so let me remind everyone in the math, when we implement the governing equation for phase field evolution, there is 1 term. So the third term on the left-hand side is the derivative of the strain energy density with respect to phase field or with respect to damage. So that's what we are going to define in this material. So, and then later on in the kernel, we will be retrieving this derivative from within the kernel and then define the corresponding residue. And same thing here, this API is also provided by the derivative material interface for us to declare some material derivative. So in this case, it's the derivative of strain energy density with respect to the phase field. Yes?
So going back to the derivative material interface, you wouldn't need that, I guess, so like for the DG, that derivative is coming only from the stuff you're about to write in this source file, right?
You mean DG?
Underscore DG, yeah. So there's nothing inherited from tutorial 10 when you're defining DG. So you wouldn't need the interface for that, but you need it for DW.
So correct, and well, well. So you are correct in that there's nothing in DG that we're inheriting from tutorial 10. Okay, this is new in this tutorial, but this, remember the difference between get and declare, right? Get means that this property is computed by someone else, and in this case, it is being computed by this guy, right? So remember in the input file, we specify the derivative order equal to 1. So the function parser will automatically take derivative of this expression with respect to the coupled variables. So in this, Yes, but to retrieve that, I recommend you to use the interface. But there are other ways. But this is the recommended way for retrieving that derivative.
So I guess the one thing that's throwing me on is the derivative material interface. It's the template. It's tutorial 10 stress. I guess why? Maybe it's a C++ question. Why is it just tutorial 10 stress? I've heard what I'm trying to ask.
It's template.
It's template.
Yeah, so for this case, it's template as this material. So it can be current. The template can be different.
Yeah, the point of this interface is to provide additional decorating methods to the object that's being templated. Right, so for example, in this case, we are adding some additional decorating methods to this object. Okay. Right, so this can be, well, the reason why we implement it this way is because these methods should be available to material objects. It can be available to kernels. It can be available to user objects. Right, we don't want to create different copies for different purposes. This is the way to do that. This is a standard C++ pattern. I don't know if you still learn that in your C++ course. Yeah.
So yeah, the C++.
Yeah. Yeah. Okay. Okay, so now let's implement the compute QP properties method. Oh, that's a lot to implement. I guess I'll just copy from my repository. Yeah, I mean I guess this has to happen for the inaugural workshop. I'll make sure we have a reasonable amount of work in the future. Tutorial 11 stress. Well, so let me copy these guys. Okay, but do allow me to explain what this does. So basically, the first complicated block is computing the second invariant of the isochoric part of the right Cauchy-Green string. So that is the I2 bar here. That's all it does. There's nothing special about it. So we need it as part of the expression for the string energy density. That's why we're computing I2 bar. And then now we are with this big block here, we are able to compute the string energy density. So the string energy density is the sum of the volumetric part and the two isochoric part. The volumetric part is just K times H evaluated with the dilation at the current closure point minus 2. I want to point out that this H is not defined in this tutorial 11 stress itself. It's being inherited from tutorial 10. Right, so that's the magic of inheritance. And for the isochoric string energy densities, I'm just basically copying the mathematical expression for string energy density. There's, I don't think there's anything special there. Once we have all the ingredients, we're able to define the string energy density as WQP equal to the current degradation function times the sum of all the components, which is the volumetric part, the isochoric part, and the second isochoric part. And that's it. That's the definition of the string energy density. But we still need to define the derivative of the string energy density here because we need to use that as a source term or the driving force for fracture propagation. So it's dW is equal to, well, the same expression, but it's multiplied by dg instead of g, and that's it. I do want to comment, if you are sort of familiar with phase field fracture method, a lot of the times people do a asymmetric split of strain energy density, namely the degradation function is only applied conditionally to some part of the strain energy density. You can for sure do that here, right? Just write your own logic here and then do the decomposition and apply the degradation to only the active part of the strain energy density. But for simplicity, we'll just do isotropic degradation in this tutorial. And we need to actually apply the degradation function. So remember, this P is the hydrostatic stress at every quadrille point. So now I want to degrade that by the degradation function. And finally, we are ready to just call the base class compute QP properties to evaluate the second and first Piola-Kirchhoff stress. Okay, and now I think what I did before is correct. We do need to modify a method, which is, so remember in tutorial 10, tutorial 10 stress, we defined this isochoric stress and volumetric stress helper methods to help us compute the isochoric part and volumetric part of the second Piola-Kirchhoff stress. So now for isochoric, for volumetric stress, we've already degraded the hydrostatic pressure, so that's taken care of. But for the isochoric part, I would like to degrade or apply the degradation function to the entirety of the isochoric stress. So I would want to inherit and modify the behavior of isochoric stress. So to do that, I inherit and will override the isochoric stress method. What's the signature? And I will mark that as override. And here, to override its behavior, it's fairly straightforward. All we need to do is to multiply the result by the degradation function. Return degradation function times whatever is computed by the base class. That's it. So we've degraded the volumetric part here, degraded the volumetric stress here, and now we're degrading the volumetric, degrading the isochoric part of the stress here. So now the stress is also degraded. Now we have the strain energy density. This is the modified strain energy density after multiplying the degradation function. This is the derivative of the strain energy density with respect to damage. And we also have the correct value for the hydrostatic pressure after degradation. This is the isochoric stress after degradation. And finally, we're using the same routine inherited from the base class to evaluate the stress. So that's how we introduce coupling into a solid mechanics material model. So we have a base model here, which doesn't know any additional physics beyond solid mechanics, right? This is a pure hyperelastic material. But now we are inheriting from the base material, and then we're adding additional coupling to the material. So, so in this case, in the case of phase field fracture, it's as simple as multiplying the stress by the degradation function. But there may be other physics that requires more involved coupling or the different forms of coupling. I think it's as long as you designed your base class in a modular fashion, there should always be a way to introduce those additional coupling. Okay, so that's which step were we at? So that's step 2. We've done step 1 in the input file. Step 2, let's modify the stress model accounting for damage degradation. The third step is to implement the strain energy density as the driving force for crack propagation. That's also done inside the material model. That's basically these 2 lines here. This W and dW is the strain energy density and its derivative for driving fracture evolution. So now the only task that's left is step 4, implement the weak form for fracture propagation. For that, we will add a new kernel. So there is a template kernel object. So the header file is here and the source file is under the source directory. Yeah, so I guess this also answers your previous question, right? So the derivative material interface, you can see the decorator cannot only be applied to material object, but in this case, we're also applying it to a kernel. So it allows us to reuse the code. Okay. I will not go over the basics again. So the only thing we're going to implement is, if you remember from yesterday, it'll be compute QP residue. Like this. Why do I hide this? I should keep this here. Register moose object, snail app, tutorial 11 kernel. Okay, so these are the necessary input parameters as well, and here is the constructor. This is where we will implement the compute QP residue for the additional kernel that drives phase field fracture evolution. Okay, so let me try to do that without looking at the answer. And so I need to look at the equation. Well, so here is the equation for the phase field, for phase field. So the first term is a simple source term. I guess it provides some barrier to crack propagation. The second term is the divergence of the microforce, where the microforce is some prefactor multiplied by the multiplied with the gradient of the phase field. And then the very last term is the source term for crack, is the derivative of the strain energy density, which is driving crack propagation. So I will include all of the 3 terms in this single kernel, but in practice, you can split different terms into different kernels to increase modularity. But here I would, for the purpose of this tutorial, for this workshop, I would just all of the 3 terms into a single kernel. So I'll say all to const all to R1. This is the first term is equal to, what is it? 3/8 GC over L. So that's test function multiplied by 0.75, sorry, 0.375 times GC over L. Right? 3/8 GC over L. Yeah. And the second term is the divergence of the microforce. So that is grad test. Well, I'm skipping steps here. We need to apply the divergence theorem for this step, but this is, I think this is straightforward. So it's gradient of the test function times 0.75 times GC times L times the gradient of damage, where in this case, because this kernel is acting on the phase field variable, and so the gradient of the phase field is just the gradient of the primary variable that this kernel acts on. So it's just grad U QP, right? Where the grad U is the gradient of damage. Okay, hopefully I did that correctly. The very last term is the simple source term again. R3 equal to test times, where is my derivative of stray energy density here? So it's underscore dW. That's it. We need to return something. We need to return the residue as the sum of all three. Okay, so that's fairly straightforward, I would say. This is the additional equation that drives the phase field evolution. It's the so-called macro force balance, I guess, in some context. So that should be all the source code we need to write for this tutorial. Remember, we need to add this additional kernel inside the input file. So we need to go to the input file. We have the degradation here. Well, we have these two kernels for the balance of linear momentum still, but we need an additional kernel for phase field fracture. Type equal to tutorial 11. Oops. Oh, I didn't compile. That's why. So I was wondering why auto completion doesn't work for me here. It's because I forgot to compile, and so the VS Code extension doesn't know I've registered this new kernel here. Oh. Oh, I see. It's because when I'm copying things over, I forgot to modify the namespace. So we need to go to tutorial 11 stress. This one should be called tutorial 11 stress, not tutorial 10. Okay, so for fracture, so hopefully auto completion is working now. Tutorial 11 kernel, great. Variable is D, where we use variable D for phase field, for the record. The regularization length is equal to 0.1. This is consistent. This is inconsistency with L here. Well, a better practice is probably to define L here as 0.1, so that later on we consistently refer to that, so that we don't make any mistake when we modify the regularization. Oh, sorry, when we modify the regularization length. So this is supposed to be a better practice. So this is the kernel for fracture, for phase field fracture, and we need the additional materials. I think for this problem, I chose, yeah, so L is equal to 0.1, GC is 2000, and psi C or WC is 10,000. I'll put material properties here. Oops. Use 80 generic constant material prop names. GC and WC, and prop values is 2,000 and 10,000. So there was a question in the Slack workspace. I could not follow the QP residue and did not find this section from files in GitHub Snail folder. Hey, Devanshu, can you elaborate a little bit more on your question? I'm not sure.
Hi, Dr. Hu. I just saw in the kernel file of tutorial 11 stress.c, you had a QP residual section at the bottom.
Tutorial 11 kernel.c, yeah.
Yeah, at the end you have compute QP residual. I could not follow it properly, so I was looking at the files copied from the Snail GitHub folder, but I did not see any QP residual there. So I was thinking that will you be copying this later or something?
Let me check. I can see the compute QP.
Oh, okay. I was looking at material folder.
Oh, yeah, that's why.
Okay,
yeah.
I was looking at 11 stress. Okay. Sorry for the inconvenience.
Okay, let's keep modifying our input file. So now that's let me see. I can just copy from the previous tutorial, I guess. So this computes the deformation gradient, and this guy computes the, well, so not tutorial 10 stress, it should be tutorial 11 stress. Beta equal to 2, bulk modulus 4,000, shear modulus 3,000. And in addition to this, we need to specify damage. The name of damage variable is D, and that's all we need. For boundary, well, so I've changed the boundary conditions slightly, just so we can model a standard mode 1 type fracture. So it's a fixed bottom, and I'm just applying the uniform displacement control on the top boundary. Okay, so there's an additional thing I want to comment. Well, it's not necessarily related to this solid mechanics tutorial workshop though, but it's more akin to just phase field fracture people. So if you want to impose the so-called irreversibility constraint, where your damage will only increase and will never decrease, this is the solver you need to use. This is called VI Newton RSLS. It is a variational inequality solver for enforcing bound constraints. It's implemented in PETSI. And in addition to that, you need to tell Moose what the bounds are. This is how you specify the bounds. This is basically saying your phase field variable cannot be smaller than its value from the previous time step. Okay, that's a little off topic because it's not solid mechanics workshop per se, but I do want to point it out. I think that's all. I think that's all I need to do, and let me try to see if I can run the input file. So here I'm running this in serial because I want to show you there will be a very slight pause at the beginning of the simulation. That is when we perform the just-in-time compilation for the derivative parsed material and then automatically taking the first order derivative. So there will be a very slight pause here. Yeah, so it'll probably take maybe less than a second or something like that. And after that, the simulation should proceed as usual. So, well, I terminated the simulation because I want to show you that I think the just-in-time compilation will provide this .git cache hidden folder here to save all of the just-in-time compilation results. So those are the machine code, as you can see. Yeah, so these are the, well, depending on your platform, if you're on a Linux machine, it will be .so. If you're on a Mac machine, probably be something like .dylib or something like that. Okay, these are compiled and I cannot see the source code. If you compile your executable in debug mode, we will keep the source code for the just-in-time compilation units, and you can actually examine the source code of the of your parsed material for debugging purposes, I guess. Well, just so you know, just so you are aware of the existence of this folder. And sometimes if you run into sometimes if you want to completely restart a simulation, so for example, right now, if I rerun this simulation, you won't notice the slight pause at the very beginning because we are just reusing what has been compiled before. But there may be cases where if you want to redo the function parsing and the derivative algorithms, you can remove the folder, remove the hidden folder, and then now if you run it again, it will you can feel the pause again because we are redoing the automatic differentiation and function parsing. Okay, so I recommend you to run the simulation in parallel because I think it will take a while. But anyways, I have an animation here showing you the results. So it's a standard mode 1 fracture where bottom is fixed. We're applying the displacement control on the top. And you can see, well, I'm using a coarse mesh here for sure, but in practice, you should refine the mesh. But I think you get the idea. So I'm showing the mesh in the top left corner, and this is the evolution of the dilation field. This is the evolution of the hydrostatic stress, and this is the evolution of the displacement field. You can see the displacement field is effectively discontinuous, even though you are using a continuous function space. I'll play. Well, so let me play it again with a slower playback speed. So here you can see stress will concentrate near the crack tip. And then once the strain energy density exceeds the critical threshold, which is 10,000 here, crack will start propagate, and well, that's what you see. Once crack is here, it will become stress-free because remember, we're degrading the stress as a function of the degradation function. And you can also see the evolution of the dilation field and the mesh, etc. I think we have some time for questions. And after that, we will take the lunch break from 12 to 1. Well, we'll reassemble at 1 p.m. Eastern time. But if you have any questions, feel free to ask them now, or I will see you after lunch. Yes.
So the parser that you use to input that to compare the degradation function, if the name of that function is identical to one of the functions that is used, would material override it, or would throw a flag?
So the worst case scenario is it will error out, but well, I mean,
I think the worst case scenario is you don't know what it's doing.
Yeah. So in a MOOS design standard, we strive to make sure that worst case scenario doesn't happen. So we never fail silently, right? So, but can you elaborate on what you mean by if the function name is the same as some other? So you mean, for example, if I define a material property here as G, and if the function name here is called G as well, you mean?
Yeah, or just, I guess here is, I mean, there's not a risk of some other function being G. But,
Yeah.
if it's
so if it is a function, for example, if it is a user-defined function here called G, Moose, I think Moose is smart enough to distinguish between them because the underlying C++ objects are different. Okay, if there's no more questions, we'll reassemble at 1 p.m. Eastern time. Talk to you later. I will stop recording and restart the recording at 1. Okay, thank you. For those of you who are looking at the video recording, I forgot to turn on the recording at the very first part of this afternoon session. So, so let me do a very brief recap. So we finished the tutorial 11, and in tutorial 12, we will learn how to use a different solution strategy, namely the fixed point iteration, to solve the phase field fracture problem. So I was trying to explain the differences between the monolithic solve and fixed point iteration. Well, the takeaway message is that for monolithic solve, you form a big equation system at every nonlinear iteration, but for fixed point iteration, you form separate equation system for different sub-problems, and you iteratively solve them to convergence within every time step. Okay, so sorry about that. So we were here, so we were trying to explain the differences between, we were trying to explain the setup for the fixed point iteration. We just went through the first multi-apps block, which basically tells Moose to create a sub-application when we are executing the solid mechanics app. And then the two transfer blocks are what we use to communicate information between the two apps or among multiple sub-apps. Okay, so the first transfer block transfers displacement variables from the solid mechanics app to the fracture sub-app. And the second transfer block transfers the phase field variable from the fracture sub-app back to the solid mechanics app. So by default, the transfer happens. So you have control over when to execute the sub-app and when to perform the transfer. And in this case, I think the default behavior is that if you don't specify execute on flags, the default behavior is it will execute the solid mechanics app first, so you solve for the displacement, and then it will transfer the displacement variables to the fracture sub-app. And then it will start the fracture sub-app, solve for the phase field, and then after that, the main app will retrieve the solved phase field value from the sub-app back to the main app. And then that's the default setup, but you have a finer control than that through the execute on flags. Okay, so these are these are really the two additional blocks you need to specify in order to set up a fixed point iteration. But regarding the executioner block, remember the executioner block controls how Moose solves the problem, right? So because we're using a different solution strategy, we need to specify some additional arguments here. So the first argument here is fixed point algorithm. So we have different fixed point algorithm implemented. The Picard algorithm is the one that I have been describing. There are other variants aiming at accelerating the fixed point iterations convergence. rate. But here we will just stick with the most basic strategy. And for fixed point max iterations, I'm specifying 100, meaning that I will iterate between the different the two sub apps at most 100 times. And this argument here, except on max fixed point iteration equal to true, means that once I hit that 100 fixed point iteration, I claim, well, the solution is sufficiently converged. Why don't I accept the solution and move on to the next time step? And if you say except on max fixed point iteration equal to false here, it will reject the solution if you hit the max fixed point iterations and then mark the current time step as failed. And then it will restore the solution to the previous time step, cut the time step, and repeat the time step. Hopefully that will converge. So that's what these two parameters do. And then these two additional parameters control the tolerance when we can say the fixed point iteration has sufficiently converged. Yeah, and then this is the default behavior. I think it just looks at the norm of the entire solution vector to determine convergence, to check whether or not the norm of that is below the given threshold, below the given tolerance. And there are ways to modify this default behavior, but we will just be sticking with this default convergence check here. And in the fracture app, you can see it's mostly the same input file. Just we're just separating out the input file from tutorial 11 to two parts. The fracture is the relevant part for the fracture subproblem. Yeah, and I think that's all we need to set up the fixed point iteration. Now, let me actually run it, and so you can have a better idea of what fixed point iteration does. So first of all, again, you can see that I have two input files here, a tier_mechanics and tier_fracture. I will be using the mechanics as the main app because that is where I set up all the multi-apps and the transfer. And then it will, because I have that multi-app block inside the mechanics input file, Moose will know to read this input file called tier fracture and instantiate another application on the fly. So this is how you call this is how you run the simulation. There's nothing different. When you run it, you can see. Okay, so I want to pause here and explain what's going on. As I mentioned earlier, it will create two apps, one for the main app, which is the mechanics app, and one for the fracture sub app. So first of all, what you see here is the summary, the regular summary you see for the mechanics sub app. And you can see here the variables column here. We only have this x and this y. Damage is not in this equation system. Okay, and then the next block, what we see here is the information from the fracture sub app. Okay, it uses the same mesh, but here you can see that in the nonlinear system, the only variable is the phase field damage, right? And if you paid attention here, you can see that in the main app, damage belongs to one of the aux variables. And then in the fracture sub app, disp x and disp y belong to the auxiliary system. We set up those auxiliary variables to receive information from the other app, basically. Okay, so now we're at time step 0, nothing happens. At time step 1, you can see some additional console logging to help you understand what's going on. So initial fixed point residual norm. So this is the starting norm of the residual at the beginning of at the 0th fixed point iteration, and well, I think well, maybe the default has changed. So now we solve the fracture sub-app first, and after that, we go back to solve the mechanics app. Okay, and then what happens in between is the fracture app solves for the current damage given the frozen displacement field. It transfers the damage back to the main app, and then the solid mechanics app is using that frozen damage field to solve for the current displacements. And you can see here is a summary of the convergence history of the Picard iteration or the fixed point iteration. So we didn't make much progress in the first Picard iteration, and we solve for then we start the next sub iteration inside fixed point iteration. So we solve for damage again with the updated displacement field given by the mechanics solve. And then again, it transfers damage back to the main app, it solves for the mechanics app. Now notice that it converges right away because, you know, during the previous phase field solve, we didn't update the damage field. And so when we transfer the damage back, there's nothing to solve for the mechanics subproblem. And so it converged right away. And the Picard iteration is able to see that, and it thinks, well, we're no longer making any progress in you know, solving the coupled problem, so I'll mark that as converged. So that's how this well, so I think this is the same, pretty much the same as the flow diagram I showed on the slide. So that marks the convergence of one time step. So that's time step 1. And then after this, we execute all the post processors and then move on to time step 2. And then we restart the fixed point iteration procedure. Yeah, and that's pretty much everything I want to talk about regarding fixed point iteration. I want to, well, again, I want to reiterate the multi-apps system and the transfer system is much more powerful than just fixed point iteration. You can do it. It's a very flexible system. And then there's one application that I forgot to mention is stochastic tools module. So at the very beginning of the workshop, I showed you a list of MOOS modules, and stochastic tools is one of them. So I mean, well, Dan is more familiar with that module than I am, but so basically for uncertainty quantification or similar applications where you need to run a lot of forward simulations, we use that. We rely on the multi-apps system as well. So basically, we have a main driving application, and then that keeps sampling. You know, that keeps dispatching new sampling sub simulations to perform uncertainty quantification. And a similar strategy is used within the optimization module as well. So, for example, when you do inverse optimization, you also need to solve many forward problems. So that they also rely on the multi-app system. Well, anyways, my point is the multi-app system is much more powerful than just fixed point iteration, but what we covered is one example usage of this system. Any questions?
Is there any capability of doing multi-mesh, or like, for example, when you solve one problem on one mesh and then I guess another app on the other mesh, or they
yes.
should?
Yeah. So well, so depending on the actual problem description. So if you so if they are just different discretization of the same computational domain, well, so it's just maybe different mesh refinement, for example. Yes, that is possible. That you can just use a different transfer for that purpose. It's so, for example, you can use multi-app projection transfer. I think. Well, so let me open the documentation. And then there is a second case. I will go into that just in a minute. You look at the list of available transfer objects. Yeah, so this multi-app copy transfer is the one we just used. And if you have different meshes discretizing the same computational domain, then you can use, for example, mesh function transfer or interpolation transfer, nearest node transfer, things like that, right? And so that is the first case where you use different meshes for the same underlying computational domain. But there are also cases where well, your problems are just being solved at different scales or with different computational domain. That is also possible, and it is the user's responsibility to define what information to communicate among the apps. So, for example, I mentioned that earlier. For if you use do a multi-scale simulation with the FE squared method. Essentially, what you want to do is, in the main app, you want to solve your mechanics problem as usual, but at every quadrature point, you will want to solve for you will want to run a sub app where you apply the deformation gradient or some strain measure as the homogenization constraint in a sub app, and then sub app will simulate the RVE with some different mesh, and then it will return the homogenized stress back to the main app. So that will be the stress for that particular quadrature point. And you repeat the process for each and every quadrature point. That's the usual way of doing FE squared, I guess. So that's one example of using completely different computational domains across apps. So short answer to your question, yes, it's possible. And I just gave 2 examples.
Thank you.
Okay. Well, and then those were examples for, you know, multi-app simulation with different spatial resolution or different spatial domain. But we can also we can also couple applications with different at different time scales. So, for example, your main app can take time step of, you know, 10,000 seconds, and your sub app can take time step of 1 second, right? And then, so when you are solving for the sub app, you will use that 1 second time step, and then the main app will just be waiting, basically. And if there's any coupling going on, we can perform interpolation in time. You can specify whether you want to do linear interpolation in time or some higher order interpolation. So coupling coupling apps or coupling problems with different timescales is also an option. Okay. If there's no other question, I will move on to the second last tutorial, which is regression testing and documentation. So first of all, MOOS is NQ1 compliant. What does NQA1 mean? I have a external link here. So it's nuclear quality assurance. NQA1 is a type of certification. So you can certify your software to with this set of standard. So it is a very strict set of requirement for softwares in the nuclear engineering space. It's designed by the ASME. So the first bullet point, Moose's NQA1 compliance is just to show you that the quality of the software is very high. It is developed under a very strict set of rules. While custom Moose-based applications are not required to be NQA1 compliant, you can still leverage on the extensive testing capabilities offered by Moose. Well, because in order for Moose to be NQA1 compliant, we had to design and develop an extensive testing suite, as well as documentation capabilities. And my point is, for Moose-based applications, you can, well, feel free to reuse whatever is designed for Moose. And even though your application does not have to be NQA1 certified, I think those capabilities will be very useful in your development cycle. And here, let's try the most common type of testing, the so-called regression testing in our snail application. So first, let me explain what regression testing is. So, well, a direct quote from Wikipedia: regression testing is rerunning functional and non-functional tests to ensure that previously developed and tested software still performs as expected after a change. So it's a little convoluted explanation of regression testing, but basically what it says is that if some capability of your application is working, we need to make sure it keeps working after changes over time, right? And if some capability of your application, well, so if some use cases of your application is not allowed, or some use case should fail, that should keep failing after we make changes over time. So that's what they mean by functional and non-functional tests, right? With the help of regression testing, our app is ensured to work and stay working. Well, that's restating what I said before. Well, so here I will set up an regression test for you to give you an idea of what it does. So to create a regression test, just so for example, we go to tutorial 13. Let's say we want to set up a regression testing for this phase-field fracture problem. So here's the input file, and now let me create a new file called tests. So this is the special file name for Moose to recognize the existence of tests, right? So in the tests file, we can specify the set of requirement or the type of the test to perform. So in this case, well, so again, we use the same heat format, so it's convenient. The type of test is called exodiff. And I think I mentioned this briefly yesterday at the very beginning. So exodiff is a type of test to, well, so basically diff against, diff your Exodus file against another Exodus file. And in this case, we use exodiff to compare our newly generated result against a reference Exodus file, where that reference Exodus file is something that is known to be correct, or it is something that we have verified. Okay. By exodiffing these two Exodus files, we will be able to tell whether something has been regressing after the current set of changes. And then the second argument is input equal to tier.i. This tells Moose which input file to use to generate the Exodus file. The CLI args is the additional command line arguments to pass into the simulation. Well, because here, take a look at the input file. Because the simulation will well, so it has n time equal to 0.45, time step size equal to 10 to the minus 3. We don't want to waste our life waiting for the simulation to generate results. Usually, it is sufficient to to just compare the results in the first few time steps, right? So that can be done using the CLI arcs option, for example. It basically well, so let me show you. It basically append this after the command line that you use to run the simulation. So, for example, this is the command that you will use to run the simulation. And now that CLI arcs option just append this as an additional command line argument. What this does is it overrides this option number of time steps in the input file to be 2. So the simulation will now take at most 2 steps. So if I run this, yes, sorry, 1 second. Yeah, so as you can see, the simulation terminates after 2 time steps. So it will generate an Exodus file called out.e, and we will compare that with a reference Exodus file. Yeah, what was your question?
Command line syntax. Can that be used to override like variables that you define in the input file? Like if you define a variable EBS or something, can you use that?
Yes. Define that variable? Yes. So all the parameters in the input file can be modified from command line.
But even like not even the block parameters, if you had like a variable L defined on the first one, it's not in any block. Somewhere it can.
Yeah, let me think. Yes, so the command line arguments always take a higher priority, so it overrides what's inside the input file. So then the final argument here will tell Moose which reference file to compile to compare against. Well, so since we haven't provided Moose with such file yet, if we run the test, we should see an error message. Well, let me show you. To run the test, go to the root directory and just run tests. Okay, so well, so let me reduce the font a little bit. Okay, so we ran 2 tests. The first test passed. This is the default dummy test for testing purposes. So this one has an OK there. And then the second test here failed. The reason of failure is summarized above. The reason is failed missing gold file because, well, it tries to compare the generated Exodus file against a reference file, but it wasn't able to find such reference, right? So to add such reference Exodus file, go to the directory, create a new folder called gold. So that is a reserved name for us to store reference results that are known to be correct. So so I'll just move the current output into the gold folder. And now if I go back to run the tests, it should pass. Okay, now you see 2 OKs here. And now let's say maybe 2 months from now or 2 years from now, someone accidentally modified the code in an incorrect way, and that leads to incorrect solution to your phase field fracture problem. This regression test should be able to capture that. Well, so why don't we test that here? Let me think how best to test that. Well, maybe let me just modify the input file. So for example, someone accidentally changed the bulk modulus from 4,000 to 3,000. right? So it should, in theory, generate a different result, and then the Exodus diff should be able to capture that. Okay, so as you can see, the regression test failed, and the failure message is saying failed exodiff, and it summarizes the differences. So it compares the global variables, nodal variables, elemental variables, and it tells you the maximum difference between the newly generated file and the reference Exodus file. And it even tells you which node it is and which block, which element it belongs to. Okay, so that's the general idea of regression testing. Did anyone ask any questions? Sorry. Well, maybe not. Maybe just noise. So that's regression testing. Any questions? So if not, let me move on to talk about documentation. So as our code base keeps growing, it is increasingly difficult for us to keep track of all of the documentations, because we have so many objects, so many classes, so many functions, and every class can have so many input parameters. It is a very challenging task to document everything. And so Moose has designed and developed this Moose Docs system for streamlining the creation of documentation pages. In order to, well, it's a Python package. Basically, you can directly invoke it using the Python script here. Well, so why don't I show you how it looks like? First, go to the root directory, and there is a folder called doc. Okay, so go to that directory. Run moose docs, check. So this should check for common problems that are identified in the current applications documentation. Well, the first time we run this command is probably slow, because we need to actually initialize the submodule large media, which hosts all the videos and images that we use in the documentation. But this is a one-time action, and later on it won't. We won't be doing this anymore. The internet connection here is really slow. Are you guys able to run this command, by the way? Oh, okay. So it's not just me. Okay.
I just ran into a error. saying usage moves docs.py, and the following arguments are required. Command. Let me press.
Yeah, so the command you need to run is moves docs.py and then followed by check. I'm not sure if
check.
you have this.
Okay.
Yes.
Okay, there is a check. Okay.
Yeah. So yeah, after a while, after the submodule has been initialized, it should run the check. And as you can see, it identified some problems with our current documentation. So so there are a total of 8 warnings saying some objects are missing markdown documentation. So the error message is pretty clear about that. So the page should be located at this location. A stop page can be created using this movedocs generate command. So we will listen to the suggestion. We will run this command, movedocs generate. I think there is an additional argument. Yeah, we need to tell it what's the name of our application. So in this case, snail app.
Hi, Gary.
Yes.
Can you please explain what does stub page mean?
Yeah, you will see that in just a minute.
Okay.
So so a stub page is basically a placeholder page to suppress this warning, and when users navigate to that page, they will know that documentation is under progress. I mean, so I think it'll become clear once you see the actual website. Just bear with me for another 1 minute or so. So after we generate all the yes.
Yeah, I'm not able to run that run test. Can you try it again?
The run tests?
Yeah.
So when I do run tests, this is what happens. Or maybe tell us what's going on. If I mean, show us the error message.
So the file is this saved as test?
So the file name should be called tests. TESTS for the file containing the test configuration.
Okay.
And make sure
when you okay.
And then inside that file, we have basically just one single block here saying we are using exadiv for the regression test. Or maybe if you so I think if you can just copy paste the error message into the Slack workspace, we can all take a look together. Maybe someone else can help you before I get to that.
Okay.
Okay.
Hi, Dr. Hu. I also could not follow up with you at that time, but this time I could run the run tests, and I'm getting the error of gold file because I did not follow up that. I could not understand this one as well. So I need a gold file to refer that inside the tests directory.
Yes. So if you look at the folder structure, so this is the original input file that we use to run the simulation, and these two are the files. So let me show you in the editor. That's probably easier to understand. So this is the original input file, and then these two files are the output file generated after we run the simulation. And this STS file is the file specifying which type of test we should use. And then this folder, the gold folder, is leading to that error message you are seeing. So you need, because we're using exadiv, we need to compare this output against some reference, right? And that reference is stored inside this gold folder.
Okay. And where are we getting it from?
Yeah, so for the purpose of regression testing, all we need to do is to make sure that the generated result doesn't change. So for that purpose, I just copied this file into the Gold folder, so that we can make sure that in the future, when we rerun the test, it will generate the exact same result. So that's the idea of regression testing.
Okay, so let's say I am happy with one of the model I just made. I am happy that this is running properly. So I make a gold copy of that, and then when I'm making more changes, I will just I can just make comparisons that what am I changing and stuff like that.
Yeah, exactly.
Okay.
The nice part about regression testing is that in the future, for example, you may be, well, so if you're changing something completely irrelevant, right, then you need to make sure the existing regression test should pass, right? But there are cases where you may be fixing a bug, right? So if you are fixing an actual bug in your model, then you should expect the regression test to fail, right? In that case, you need to go through the process that is called regolding, right?
Okay.
So you need to regenerate the output with the correct code after the bug fix, and then change the file inside the Go directory, and use that as the new reference. So that is the so-called regolding process.
Okay. Okay. Thank you.
Okay. Okay, so that was more on regression testing. Now, well, so we were at documentation. So now we go back to the doc folder. We just generated all the stop pages. And now if we rerun the check command, mostdocs check, it should tell us that oh, I see, sorry. After we generated the stop pages, we need to add them into the Git tree. So if you don't know how to do that yet, that's git add -a. So that's git add -a followed by the directory, which is dot. So -a will just add so sometimes you add new files, sometimes you delete files. So that -a means all types of changes. I mean, this is usually what I do, but you don't have to do exactly the same thing. As long as it works for you, it's fine. So now all the files have been added to the Git tree. Now we can go back to the doc folder and rerun the check. Okay, so now the warning has changed. So you can see log missing markdown goes to 0, but now it's warning us about some of the files, some of the documentation files are still stub files. You need to remember to actually put in your documentation. Okay, so now we're ready to generate our documentation website. To do so, just do mostdocs build --serve. So build will build the documentation. It will extract all of the documentation from the source code, and the --serve will serve the website locally so that we can open it inside our local browser. Okay, that was pretty quick. So you can see the message. So if everything went well, you should be able to see a message here saying serving on HTTPS 127.0.0.1:8000. So that is the local part for viewing your website. So if you open it in your browser, this is what you will see. This is right now it is completely empty. It has a dummy app name here. there's nothing here yet. But let me add 2 lines into the documentation page, and you will see something interesting. So go to the doc folder. There is a folder called content. So the page we saw just now is index, right? So this is essentially what we see in the browser. So there's a navigation bar and a snail app heading. That's exactly what we see here: a navigation bar and a snail app heading here. So here, let's add some more information here regarding our application. For that purpose, let me copy from my GitHub repository. Okay, so I've added 4 more lines. So this line here is a subheading with title "My Custom Kernels," and here I'm listing all of the kernel objects in our application. And the next line says "My Custom Materials," and this line lists all the material objects in my application. So if I press Control S, it saves the documentation page, and it should automatically re-render in the background. And then if we go back to our website, you should be able to see the list of kernels and list of materials that we've added in the past 2 days. Okay, so for example, if I click on this one, tutorial 01 kernel, it should open up the start page that was well, Pawan, you were asking what the start page is. This is what's inside that start page. I would say it's a boilerplate for your documentation. There is a warning here saying construction undocumented class, but it's basically saying this class hasn't been documented yet. But we've already populated many of the useful information about that object. So it tells us which parameters are required by this kernel, which parameters are optional, and also it has lists of advanced parameters. So for example, if you click on component here, so this, well, try zooming a little bit. So if you expand the component tab, it tells you the C++ type of this parameter, which is an unsigned integer. Well, it's controllable. We haven't covered that in this workshop yet, but feel free to learn that from the documentation. And then description is the description of the parameter, the component of the residue to evaluate. So this is not some magic description generated by AI or something. This is literally what we wrote. So if you go back to the source file, tutorial 01 kernel.c, remember when we were registering this parameter here, this line, we registered this parameter and we also provided its corresponding documentation here. And this is exactly what shows up here, right? The component of the residue to evaluate. And similarly, it applies to all the other parameters. So that's why I would recommend everyone, when you're writing your source code, remember to add documentation for your class, as well as documentation for each and every input parameter. So this will save you a lot of effort in terms of writing documentation. Now, all you need to do is to fill out additional information here. Well, in fact, we already have a one-liner class description for free. The kernel models a linear elastic solid. This is the class description string that we added here. Okay, so here you can, for example, add the mathematical expression of the kernel, or well, why don't I show you how to do that? So for that, you need to open the start page, go to content source kernels tutorial 01 kernel, and then here I'm deleting that construction message because I'm actually documenting it. I will say this kernel implements the weak form test function. I will just use, I guess I'll use phi I comma j, then stress ij, where stress is equal to lambda times strain ij plus 2 mu something like this. Just to show you, we can write the tech expressions here as well. So now I've saved the file. It should automatically re-render in the background. And now if we go back here, well, this is it. This kernel implements the weak form. This is the bilinear form where stress is equal to, well, that was incorrect. Yep. Now this is a fully documented class. So now if your user navigates to this page, they will know the underlying mathematical expression as well as what this kernel does, and then they can also know the required and optional parameters that they can use inside the input files. Okay. And then the same thing applies to other objects that we have created in the past 2 days. Any questions? And so once you're able to so once you're satisfied with the locally served website, you can then use the same utility. You can use MoveStocks, build, and then you can save the generated web page to a local folder, and then you can deploy the web pages to some web hosting service. For example, GitHub Pages, that's a very robust static web hosting service. It's also free. That's actually what I use for many of my projects. And an example documentation website, well, because we're looking at phase fracture problem now, so let's take a look at the documentation website for a mousse-based application called Raccoon, which specializes in phase field fracture problems. So this is the this is what the website looks like. You can design your own logo, a one-liner description of the application, and maybe some fancy animations showcasing what the application can do. And then you can also put a bunch of theory documentation, tutorials, getting started page, and documentation. So here, let me show you. Yeah, so these are all the objects you can use inside this application. Yes, David.
When you look at the parameters, look at any of these, there's what delineates. I know delineates required and optional, but what delineates advanced parameters when you're setting up?
Oh, good question. So when you are writing source code, you can register some parameters into those parameter groups. So there are in this case there are 2 additional parameter groups associated with this object. There's an API for you to do that. So it'll be something like I don't know, params, maybe register, parameter group, something like that. I don't remember the exact API, but it will be something like this. So for example, if you want to say component is an advanced parameter, this is how you do that. You can also create your own parameter group for the record. Any other questions? Does everyone have your website working now? If you run into any issue, again, feel free to leave a message in Slack. Okay. So now we're ready to move on to our final tutorial for this workshop. So this is tutorial 14, external material models. So we have implemented our own material model for a nearly incompressible new Hookean solid and its phase field fracture coupling. So those are two custom materials. So those were implemented in MOOS. Right? So we oftentimes call them native or MOOS native or internal material models. They rely on the MOOS material system. But that's not the only material model that MOOS supports. We also support, well, it's basically infinite possibilities over there, because MOOS is open source and it's just C++. There's no magic behind it. As long as you can somehow incorporate your own third-party material model and link that to your own application, you can call it an external material modeling capability, right? So here we will demonstrate. So here I will introduce two external material modeling capabilities in the solid mechanics module, and I will try to focus on NEMO2. But I do want to first tell you that we are able to use Abacus UMAT. It's a Fortran file describing your custom material model inside the solid mechanics simulations. The entry point is called Abacus UMAT stress. So it's fairly easy to use. All you need to do is to add a block called Abacus UMAT stress, and the key parameter is this plugin. You need to specify the path to your Abacus UMAT plugin, and the MOOS solid mechanics module will use that as the material model. So that is Abacus UMAT. I guess that's too easy to use. So I probably don't need to show you an example input file. And for the second type of external material model library, I will go into more details about it. It is called NEMO2, and the entry point to the NEMO2 material model is in a special reserved syntax called NEMO2. So it sits parallel to physics, solid mechanics, for example. In your input file, you have maybe physics, solid mechanics, and then boundary conditions, initial conditions, kernels, things like that. And then parallel to all of them, there is a separate block reserved for NEMO2. It is written in C++. It also uses the HEAT input file format. So if you like the Moose input file format. Nemo2 uses the same input file format, so it's, I guess it's convenient in some cases. It supports the full set of multiphysics coupling. It's very easy to set up multiphysics coupling in your material model implemented in Nemo2. It can utilize both CPU and GPU. This is, I know this is probably a game changer for many of us. It also provides a companion Python package for us to run standalone material models outside the context of finite element. So, for example, if you implement a Moose native material model, oftentimes you want to experiment with, or you want to examine the behavior of the material model on its own without solving any finite element. To do that in Moose, you have to set up a dummy cubic element and then apply the equivalent boundary conditions to simulate that. But that is not, that's probably, well, that's also very straightforward. But it would be nicer if you can directly call the material model from outside, for example, within a Python script for you to, play with your material model before deploying that inside some finite element simulation. Okay, so before I introduce Nemo2, I want to just explain why material modeling on GPUs. I want to answer this question in general. So nowadays, many of the new high-performance computers, the so-called exascale supercomputers, they are hybrid. They not only have a lot of high-end CPUs, but every compute node is also equipped with one or multiple high-end GPUs. And last year I was writing a proposal to use Argonne's. This is probably the largest supercomputer now. I was writing a proposal saying I want to use part of its allocation, and my proposed idea is to run some Moose-based application on it because it scales very well. So I can fully utilize the capability of this supercomputer. But they are not happy with my proposal because at that time we didn't add any GPU capability yet in Moose, and so they asked the question, how are we able to utilize all those GPUs on our supercomputer? I wasn't able to address that, unfortunately, at that time. So from that point of view, it is important for us to at least explore how we can run finite element simulations utilizing some of the GPU computing resources. And just as an advertisement here, the Aurora has unified memory architecture across CPU and GPU. It has more than 21,000 Intel Xeon CPU Max series and more than 63,000 Intel data center GPU Max series. It's a very powerful GPU. And here is a video. It's probably very old. It's from 2009 or something. But I think it is a very nice video demonstrating the difference between CPU and GPU. If you're not familiar with the differences yet, and in a funny way, I would say. So this is just a 1-minute video. So I'll just play it here. Well, that was an interesting video. I'm not sure for those of you online if you can see my video, or I don't know if the audio is working or not. But if just in case it didn't work, you can go to the link for the slides and watch the video on your own when you have some time. So basically, what happens is when you want to paint a smiling face there, if you use CPU, it will paint 1 pixel at a time basically, and your CPU can be very powerful, so it can be fairly fast. But with GPU, the idea is different. You do all of the so-called vectorize all of the painting jobs, because painting a pixel is the same task as painting another pixel at a different location, right? So this is the same underlying task. So there's no reason why we can do them all at the same time with a massive parallelization. That's the so-called vectorization, and that's what you see when they paint the Mona Lisa. They so basically they preload all of the paints for each of the pixel and then launch them all at once. That's what happened. And then in terms of material modeling, it's the same thing. So think about all those painters over there. You need to first prepare the string for every pixel, basically for every launcher, and then you need to go through the material model, and then the material model should spit out the stress, right? So it's the same underlying task. There is no reason why we cannot vectorize it, right? So that's the idea of GPU material modeling. And I have another sort of demonstration to give you a more concrete idea of CPU versus GPU. So on the left, I will show an animation for simulating a mechanical deformation of this weird specimen with a elastoplasticity material model. I think it's a Shiboshi plasticity with 2 back stresses. So it's a decent. It's not the cheapest material model, and it's not extremely expensive either. It's some material model suitable for demonstration purposes. And on the left, this is using 4 CPUs. On the right, this is using a single I can't remember now. I don't remember if I ran it using a 4500 or 500. I can't remember. But this is one single GPU. So on the left, what's going on is I'm using this pixel-like animation here to demonstrate the quadrature points or the elements that have completed its material update. And we see 4 different colors. It's because we have partitioned the domain into 4 different blocks, and that each CPU is responsible for a threaded update, a threaded loop over all of the elements in the corresponding partition, and perform a material update at each element and each quadrature point. And on the right, I'm showing the GPU update, where as you can see, there's no apparent pattern in this update, because there's no partition we need to do. We just need to prepare all of the input for all of the quadrature points. So in this case, it's the strain, right? We just need to prepare the applied strain at every quadrature point, and then send the task to GPU. The GPU will be able to run the material model for all of the quadrature point at once, and give back the stress at every quadrature point. So it's so this is another demonstration of CPU material modeling versus GPU material modeling. And oftentimes, yeah, sorry.
And then if on the left the colors were representing the partitions, what are the colors representing on the right?
On the right, yeah, that's a good question. For GPU, there is the concept of optimal batch size. So I need to explain what batch is first, I guess. So when you paint one pixel, that is considered to be a single batch. Right? When you paint 1,000 pixels at the same time, the batch size is considered to be 1,000.
Yeah.
So if you have a mesh with 1,000 quadrille points, then the batch size will be 1,000. Right? With GPU, because it's due to its excellent vectorization support, performing material update for a single batch is oftentimes as expensive as performing material update for 1,000 batches at the same time, right? So it's not a linear complexity; it's free lunch, right? Updating 1,000 material points is equivalent to updating one. But that story isn't always true, because there is the so-called optimal batch size, which is the maximum bandwidth that your GPU can process. Right? There has to be a limit there, because we don't have infinite resources on GPU. So usually it depends on the complexity of your material model. If your material model is very expensive, the optimal batch size will be smaller. But if the material model is cheaper, the optimal batch size will be larger. So before we reach the optimal batch size, let's say the optimal batch size, for example, is 2,000, right? So anywhere before 2,000, well, anywhere smaller than 2,000 batches, we still get that free lunch, the quote unquote free lunch. But once we perform material update with a batch size larger than that optimal batch size, we go back to optimal, we go back to linear scaling, basically linear complexity. So it's basically like a for loop. Right? So we want to do a material update in smaller chunks so that the batch size is smaller than the optimal batch size. So that is what the colors mean on the right, in the animation on the right. So I think in this case we have 4 colors as well. So we're splitting all the quadrille points into 4 batches. Each batch is, for example, 500 points, and then we send them to GPU one by one. We do that 4 times. And then it's sort of randomly scattered, because there's we don't have to contiguously select all the batches. That's my point. As long as its memory is contiguous on GPU, that should be fine. Yes. Which one?
So that one includes the solid or just the assembly?
Okay, so for those of you online, the question was, does this account for the time in solving or just the time spent on the material update? So for these 2 animations, I'm showing the total wall time, right? But that is a good question, because so right now we are only, well, using this NEMO2 material modeling library, we're only vectorizing material update, right? So it's only beneficial if a big chunk of your total wall time is spent on material update, right? If, let's say, 90% of the time of your total solution, time to solution, is spent on the linear solve or matrix vectorization from PETSI, then there's no advantage in using a GPU material modeling library there. Well, at least it won't play a big role. It won't give you a lot of speed up. But for this specific setup, because due to the complexity of the material model, a lot of compute time has been spent on doing the material update. And so a GPU material modeling library can accelerate the simulation, the overall simulation speed. And then, well, in the future though, because as I mentioned earlier yesterday, PETSI also starts to provide some GPU support, and so there's technically nothing preventing us from utilizing those GPU support in our MOOC simulation, right? So the solver, the linear solve part can utilize GPU in the future, I would say. And then the only part that's left is the finite assembly part, which MOOC is also trying to expand support for. Sorry, what?
I mean, you mentioned this one A500 GPU, but I assume you're still using full NPI.
Yes and no, because for the material update, for the purpose of this demonstration, the material update is not using CPU at all. So CPU is only used to prepare the input for material update. For example, compute strain from displacement gradient at every quadrille point, and put all of the strain into a big batch of input.
It's a total type, including the solid. They're not using the NPI for the solver.
I mean, this animation should be scaled according to total wall time, I think.
Yeah, I think you should use seismic because your solver is not GPU seismic.
Yeah. Yeah, that's a fair point. Yeah, though the time spent on solving the system of equation is a relatively small portion in this example, but yeah, that's probably a better idea for a fair comparison.
Hey Gary.
Yes.
I have a quick simple question. So is there a comparison between the time to communicate with the CPU and GPU? Is it the same or it's different?
It's very different. I mean, transferring data back and forth between CPU and GPU is considered a significant overhead, unless you use some of the recent architecture like APUs, something like that. So that brings us to an interesting situation where if your material model is very cheap, for example, if all you do is linear elasticity, for example, then it doesn't make a whole lot of sense to use GPU, because what you have to do is to collect all the information needed for the material update, send those data from CPU to GPU, and then use GPU to perform the update, and then grab the output back from GPU onto the CPU. So there is if your material model is too cheap, then that transfer overhead will actually kill the efficiency. So that is one disadvantage of this hybrid approach. But I do want to comment that this will hopefully change in the future as when we have the complete picture for the complete GPU picture for the MOOC ecosystem. So, for example, if MOOC assembly and material update and the PETSI's linear solve can all happen on the GPU, then there won't be any communication between CPU and GPU unless for outputting purposes, right? So if all your data can live on GPU from the beginning to the end, such overhead goes away.
Understood. Thanks.
Okay. yeah, I guess that was enough advertisement. Now we should actually learn how to use NEMO2 and MOOS solid mechanics module together. So there is indeed an additional dependency because NEMO2 is developed based on PyTorch. That's a very popular machine learning package developed by Meta. NEMO2 uses the C++ backend of PyTorch, which is called libtorch. Well, let me try if this installation procedure works or not, because I don't think I extensively tested it. So first of all, inside our Conda environment, remember we've already installed all the development dependency for MOOS. So now we're installing an additional environment dependency for NEMO2, which is PyTorch. Well, hold on. It's probably a bad idea to do this. Well, just for my sanity, I will remove the environment and recreate a new one. But you don't have to do this. I did something else yesterday. Okay, now I'm installing PyTorch using Conda. Oh, by the way, this is only supported for Linux and Mac systems. If you are on a Windows, I'm not sure how to do this. And for I think there's, well, because this is very experimental. I think there is some dependency issue if you're using if you're using Mac Silicon. If you run into installation issues, please let us know. That will be precious user data for us, so that hopefully we can improve the installation process in the future. So I've installed PyTorch in my environment. Well, just for checking, let me run Python and let's see if I can import Torch. Oh yes, I can. And while we are here, let's print out print Torch path to see where Torch is installed. Okay, so it's installed here. Now we can go to MOOS and then configure MOOS by passing our torch directory to -- with libtorch command. So we go to MOOS. Configure -- with leap torch equal to, then we pass the path to, oops. We pass this path to the PyTorch installation to this with leap torch argument here. So that's configured. So now we've effectively configured Moose to use leap torch, and now we should enable the Nemo2 submodule in Moose using this command. So git submodule update recursive checkout init module solid mechanics contrive Nemo2. So this will grab the latest version of, well, not latest, the current compatible version of Nemo2 as a submodule in Moose. Okay, now if we go back to our application Snail and recompile, we should be able to see that yeah, this should recompile, yes. And now you can see some source code inside the Nemo2 directory compiled. So that's a good sign that we've successfully enabled Nemo2. And then while this is compiling, I think it's actually a good opportunity for you to get a brief overview of what Nemo2 can do. You can take a look at the names of all the source files. You can see that we have various time integration routines, linear elasticity, as well as crystal plasticity, as well as various hardening models, the Voce hardening, Shiboji hardening, and different flow rules associated with kinematic hardening, rate independent plasticity using the return mapping algorithm. Yeah, so that I think that's a decent overview of what Nemo2 has. But for a complete documentation, please refer to the Nemo2 documentation website, which is included in the is included on the slide. Yes. No, unfortunately, I mean, right now everything in Nemo2 is maintained by me and another developer at Argonne. So, yeah, so hopefully, once Nemo2 becomes more stable, or the physics developers will chime in and import more physics module here. But right now, Nemo2 is only integrated into the solid mechanics module, which is why I'm, covering this in this workshop. Yeah, usually we run the full set of verification for all of the models in Nemo2. Well, I have to clarify, for some of the material models, it is actually using different formulations than what's used in the Moose native solid mechanics material modeling library. So there will be differences in terms of results if we're actually using different formulation. For example, I think for crystal plasticity, the formulation used in Nemo2 is slightly different from what's used in Moose. But for other types of models, I think they should be mostly identical. And for the record, the formulation in crystal plasticity is based on the multiplicative decomposition, the FEFP decomposition. And in NAMO2, it is, well, it is still FEFP decomposition, but it's we do some additional we make some additional assumptions to make it additive. Huh? No, yeah, it's still using the multiplicative decomposition, but there are some additional assumptions there to simplify the that should be available in the full documentation. And is the installation time for everyone? Okay, cool. And then while this is installing, I guess I can skip ahead and introduce you to some of the main features of NAMO2. So first of all, I've mentioned too many times. The full name of NAMO2 is New Engineering Material Modeling Library version 2. It's version 2, so there is a version 1, but version 1 is actually using a different name. It's called Nuclear Engineering Material Modeling Library because the version 1 library focuses on nuclear materials, and the version 2, since we've expanded the capability to multiphysics modeling, it's no longer limited to the set of nuclear materials that we have worked with. So we're rebranding it as the so-called New Engineering Material Modeling Library version 2. So anyways, here's the official documentation. Here are some feature highlights. All the material model implementations are compute device agnostic, meaning that you write your material model in C++, and as a developer, you don't need to worry about whether this model will be used on a CPU or on GPU. You don't need to worry about anything about the compute devices. You just focus on the definition of the material model, and everything else is taken care by the NAMO library. The model archival also uses Heat, so it's the same input file syntax as Moose, so that makes it convenient in some use cases. NAMO2 also supports arbitrary model composition, meaning, well, I will show that in the next slide. Basically, it allows for developers to write extremely modular code for material models. And we also support general purpose multiphysics coupling beyond just solid mechanics. But right now, the only physics module we have implemented is solid mechanics. And we also, well, so this is the second last bullet point is probably the most interesting to many of us. NAMO2 can, because it is built upon LibTorch, the backend of PyTorch, it inherits a lot of the common machine learning strategies used in the machine learning community. So namely, they have LibTorch is a very powerful library for backward automatic differentiation. So we are able to so it's slightly different from Moose AD, right? So the AD used in Moose is the so-called forward mode automatic differentiation, and it is able to give us the derivative of, for example, stress versus strain as a function of strain, right? But with AD implemented in NAMO2, you're also able to get the derivative of stress with respect to the parameters, and by parameters I mean Young's modulus, Poisson's ratio, things like that. So you can get the derivative of the model response with respect to the parameters. So that is significant because in many of the optimization algorithms, or if you're coming from the machine learning community, the training algorithms requires information about parameter derivatives to to perform the update. So with that, you're able to, for example, implement a material model in ML2 and then train that, quote unquote, train that or optimize that against some experimental data to find the best set of parameters. And the last bullet point is just telling you we are currently developing a Python package for you to use the same input file and then inside Python instead of C++, so that you can use the same set of input file to to do both training using some Python-based machine learning libraries, as well as use the same input file in some finite element simulation inside Moose to to perform material update. So that's a brief overview of library. And I want to, well, let me check if my installation was successful or not. Okay, it completed for me as well. For the solid mechanics module in ML2, we currently support elasticity, plasticity with macro scale consistent plasticity, Presina viscoplasticity or creep, as well as the recently added crystal plasticity. And we have a big gallery of hardening models. Just to name a few, we have the commonly used the linear isotropic hardening, Voce, kinematic hardening, back stresses, the Shiboshi model, and so on. We also support two ways of doing return mapping: the scalar valued radial return algorithm for J2 plasticity, as well as the general return mapping, where you actually solve a bigger system of equation, including stress or strain. And well, so the last column there is you want to update the material for finite element. In the context of finite element, it's mostly strain control, right? So you pass strain as the input and the model stress. But there's nothing preventing us to say we provide stress and the model give us back the strain as output. So that's the two types of control. This is useful for many of the material modeling applications, such as simulating some stress-controlled experiments. The system is very modular. You can literally pick any of them and compose them together. So we have a total of 65. We will have 65 forms of different material models implemented just with 400 lines of actual C++ code defining the material models. It's very modular and it's customizable and extensible. Okay, so now I will give you an actual example of writing a ML2 material model and then calling that inside using the solid mechanics module. So say this is the description of the material model. I deliberately make it complicated just to demonstrate that it's modular and it's easy to implement them in ML2. So the first column is saying we have a general yield function with isotropic hardening. We have the isotropic Mendel stress and the standard J2 flow with the von Mises stress as the stress measure. We have linear isotropic hardening, and the fourth equation is the definition of the yield function. For the second column, the model also has Persina viscoplasticity with associative flow. For associative flow, the direction of the stress evolution is coming from variational statements. So the flow direction is equal to the derivative of the flow of the yield function with respect to the Mendel stress. And similar rule applies to isotropic hardening, and similarly to kinematic hardening as well, but we are not including kinematic hardening here. And then this is the expression for the standard Perzina viscoplasticity, or some people refer to it as the power law creep model. And this is the associated update of plastic strain and equivalent plastic strain. And for the purpose of demonstration, we'll just use linear isotropic elasticity. And we use the general purpose return mapping algorithm to solve the system of equations to update both stress and equivalent plastic strain. Okay, so this is the mathematical description of the material model, and it's very easy to implement them in NAML2 because you just need to focus on one specific equation in a single material model. And so, for example, the first column, we have 4 equations here, and so they translate to 4 NAML2 material models. The first one is isotropic Mendel stress. I mean, their names are pretty self-explanatory. The second one, SR2 invariant, symmetric rank-2 tensors invariant. The third equation is linear isotropic hardening. The fourth equation is called EU function. Similarly, for the second column, third column, and fourth column. And NAML2 has this powerful model composition capability. So once you implemented all those models, you can throw them into a composed model, and NAML2 will automatically sort out the dependency among all of models. It will figure out the optimal sequence to evaluate all of the material models. And so here I think I have an example NAML2 input file. So this is the NAML2 input file. Again, this is using the same heat syntax used in MOOS, so it should look familiar. So there is a model section to contain all of the material models that I just mentioned on the slide. You define all of them along with the material properties, and this is the composed model I mentioned. Just throw all of them here, and then NAML2 will automatically compose them into a big model. And then this is an implicit update to actually perform the return mapping. Okay, and then this is the NAML2 input file. The way to use the NAML2 model in MOOS is fairly straightforward. I just copy from here. And as I said, the entry point to NAML2 is the so-called NAML2 syntax here. The first argument tells MOOS which input file to use as the material model. Pretty similar to Abacus UMAT. You need to tell MOOS where the external material model exists. And then the second argument tells MOOS which model inside the NAML2 input file to use as the material model. So in this case, you can see it will use this final model here as the material model. Temperature is T and verbose is true. It will print some additional debugging or logging information. Mode is element. I will explain that in just a second. And device equal to CPU. It tells MOOS where to perform the material update. If you want to perform the update on GPU, you can simply say device equal to CUDA. And that will take care of everything. It will send the material model to the specified device, in this case CUDA, and then perform the material update there. And if you have multiple CUDA devices, it follows this schema, for example, CUDA 0 or CUDA 1, where the number after the colon is the device ID. And as a side note, if you want to, well, that's sort of apparent, but I have to point that out. If you want to use NAML2 to perform material update on GPU, you need to install a PyTorch that supports the GPU. It's sort of obvious, but even myself sometimes forget about that. So if you go to the PyTorch website, so remember we installed PyTorch from the Conda channel. I think by default it has GPU support if you are using the Linux system, but I'm not sure what happens on Mac. So on Mac, if we install using Conda, I think the default only has CPU support or some MPS support. It doesn't have CUDA support. Well, on Mac, you don't have CUDA support by definition. But if you're on Linux, I think the default is yeah, I think the default is with CUDA 12.1. So you can experiment with CUDA support if you happen to be on a Linux machine.
Hey, Gary, there's a question in the Slack channel. Somebody was having trouble. Looks like they had packages for both libtorch and PyTorch in their environment.
Let me open up my Slack. Yeah, I think, is this a, are you using the Mac?
Yeah.
So I think, yeah, I think this is an issue actually. So when you install PyTorch using Conda, it actually has, it actually gives you 2 copies of PyTorch, 2 copies of libtorch. Can you try this? Can you try, well, I'll type the command here. Just Conda remove PyTorch. So this will remove the PyTorch installed by Conda, and install, instead of using the Conda PyTorch, just try to install torch from pip. Just pip install torch. Let's see, and then try to recompile and see if that resolves the issue. You may need to clean the current build and you know, start from scratch, rebuild it, rebuild everything. Let me know if how that goes.
Hey, thanks.
Okay, so now well, so let's first run this once. Let's go to tutorial 14. We run the, well, further we need to run the moose input file. You cannot run the Nemo2 input file using a moose executable, just for the record. Okay, so this should run the, hopefully this should run. Oh, coupled variable oh, yeah. So I need to create a dummy coupled variable temperature here. Because for this simulation, the material model is temperature independent, so it doesn't matter what value of temperature we pass in here. But in general, we support thermomechanical coupling. Let me rerun this. Okay, so this is the solve in action. Here we are only using 1 processor, and this is a decently expensive material model, and you can see it's taking a while to perform the material update. Okay, so I'll stop here. Okay, so so now I can explain what this mode option does. So remember at the, well, so 2 slides ago, I was explaining what's the difference between you know, CPU and GPU, and I mentioned the thing called batch size, right? So the idea is the time spent on updating a smaller batch of material model is basically the same as updating a large batch of material model. And so this mode parameter here basically controls such batch size. So we have two modes here. We have mode equal to element and mode equal to all. So when mode equal to element, we'll batch all the quadrature points within one single element, and then send that to the GPU to perform the update. And you know, so if you have a 2D Q4 element with linear quadrature rule, that's 4. The batch size will be equal to 4 then. If it's a 3D hex 8 element, then the batch size will be 8. So that's not ideal because the batch size is still pretty small. And so we will want to use mode equal to all here. What mode equal to all does is it loops over all of the elements in the mesh and assembles all of the input to the material model into a big tensor, and it send it to GPU to update the material model. Well, even if you are using CPU, that is advantageous because, you know, CPU also has some vectorization support, even it's not as extensive as a CUDA device. But in theory, we should still gain a lot by using mode equal to all. So let's try that. So as you can see, it's notably faster because so this speed up, because we were only using CPU. This speed up completely comes from vectorization, right? So it's updating 4 quadrature points at the same time versus updating how many quadrature points versus updating I think it's 600 quadrature points at the same time. So that's the difference. And you can repeat the same experiment if you have access to a CUDA device by changing device from CPU to CUDA. So that concludes that. Yeah.
Is it able to take in, let's say, like a sub that is producing a value? Is it able to if it's able to material model agree with the value that comes in generated elsewhere and change itself based on that? Like it's say, I know it's not in there, but like it's say we get a damage on that. I know it's not in it, you can't do that right now, but you can change some of this.
Yeah, so that will have to happen at the so-called NAMO2 interface, right? So we wrote some glue material just to glue what we have in MOOS and what we need in NAMO2. And what you described will go into that interface where you will want to couple in an additional variable called damage into the batch material and then send that to the NAMO2 material model. But I mean, just to clarify a little bit, NAMO2 knows nothing about finite element, right? So it is nothing but a material modeling library. So you can use it in other applications, you know, other than finite element. You can use it in finite volume. You can use it in, you know, alternative quantification or whatever. So my point is, it doesn't know anything about finite element. It is up to you. In this case, the solid mechanics model is calling the NAMO2 model, and so it is the caller's responsibility for gathering all of the information needed by the material model. Yes. I think so. I think the regression has to be put into MOOS, have recovery turn on. So I think it does.
Because standard you have to, I think actually we can restart or recover, you have to use the same number IPR?
Oh yeah, so for that, yeah, I think we could. So for the online audience, the question was, does NEMO2 support restart and recover? Well, so first of all, for those of you who are not familiar with that system, restart and recover is yet another MOOS capability offered by the framework, where you can, just in case your simulation terminates, either by user intervention or maybe a soft failure, MOOS can save some checkpoint, and then you can restart the simulation from those checkpoints. That's the so-called restart and recover system. And then the question was asking, does NEMO2 play nicely with that system? I think so, and I think it could even be more flexible than that. For example, if you, somehow you're able to start with, you can do, if so, somehow if you can do end-to-end restart, for example, if you run your previous simulation using N processors and you can somehow restart it using M processors, as long as the total batch size doesn't change, you should be able to restart your NEMO2 material model update. Well, because that's the natural advantage of batched material update. You basically gather everything to a big batched vector, and so it doesn't matter how many processors you're using, as long as you're doing the correct communication.
So following to that question, so how actually restart is happening? I mean, is it actually that it can read this Exodus file with all the information about the you know, whatever the last time step or something like that, or how? Well, maybe you have an example.
Yeah, I don't have one, but I can make an example right now. So if you go to tutorial 11, I think this is the monolithic solve of the phase field fracture problem. Let's just turn on checkpoint to demonstrate this. I can do checkpoint equal to true. So it's very simple. This is all you need to turn on checkpoint and restart. So now we go back to tutorial 11. Now let me run this with 2 processors for demonstration purposes. By the way, I haven't tested it before in case it doesn't work. Well, hopefully it works. So I will run it using 2 processors, and I will.
What is the line again? Is it checkpoint?
Yeah, checkpoint equal to true. Put that to inside the outputs block, and then let me pass in an additional argument. So it's executioner num steps equal to 2. So I'm basically forcing the simulation to stop after 2 steps, just to demonstrate recover. It solves 2 steps. It stopped, and now we have a as you can see, there's a new folder. By default, the name is the name of the input file appended with _out_cp. CP means checkpoint. And then if you look at the folder, I'll show that in the editor. So if you open that folder, you will see some checkpoint files in there, where this .cpr file is. Well, I'm not an expert in this, but these are basically the information you need to restart the simulation from this point. So 0001 means the checkpoint from the first time step, and 0002 means the checkpoint from the second time step. And then this mesh.cpi is probably all the information you need to reconstruct the mesh. And then the restart-0 and restart-1 are the information you need to restart the MOOS simulation with the exact same material storage and the equation system and things like that. -0 means it's for processor number 0, and for -1 it means for processor number 1, or rank 0 and rank 1. So meaning that you should So if you ran your previous simulation using 2 processors, you can only recover it using the same number of processors, with, in this case, 2 processors. So to recover the simulation, you use the same command. So now I will remove the num steps equal to 2 constraint there, so that simulation keeps running, and you add -- recover. So this should automatically read all of the checkpoints and then restart the simulation from that point. Okay, so as you can see, it restarted from time step 3. It'll keep going.
That's very nice. I think there should be some kind of a parameter because, for example, if you have some very large simulation and you don't want to blow up the available space, so like the frequency that you save these checkpoints, I guess.
So yeah, so that's a good question, because all of the parameters here, they are the shortcuts, right? So these are shorthand notation. For example, for Exodus, instead of doing this Exodus equal to true, you can create a subblock here and then say type equal to Exodus, and you have finer control here. You have a lot of parameters to control the behavior of Exodus outputting. Similarly, for checkpoint, you also have finer control. Well, so let me say CP type checkpoint. You can say interval. That's what you mean, right? So you can say interval equal to 10, or yes, I'm getting to that. You can also say number of files to keep. The default is 2, so it will keep the 2 most recent checkpoints with an interval of 10 with these 2 parameters here. You can say you can increase this to 5, but I don't think there's any benefit in doing that. And interval equal to 10, it's just outputting the checkpoint less frequently. Okay.
Oh, that's very nice. Thank you. Regarding the decomposition between the processors, I guess also there should be some kind of tool that, for example, as you mentioned, that if you run it with like 2 processors, then you're able to restart it with 2 processors. So I guess there should be something that can convert it to like I don't know, the generic state, and then decompose back to more processors.
Yeah. So what you are describing is the so-called N2M restart. I think that is an open research question. So how best to do that, efficiently, both in terms of time and memory, I think it's an open question. There is some prototyping. There is some prototype implementation out there, but I don't think we have that in use yet. And I mean, if at some point, the community.
Hello.
Well, anyway,
somebody else just forgot to mute.
Yeah. So if at any point the community has converged upon the so-called best solution, there's no reason why we can't implement that in use. Okay. But for now, yeah, the only thing we can do is N2M restart.
Yeah. Yeah. Thank you. But also, well, a very generic question regarding the actual decomposition, how it's happening. So, is there any control that like to make it more fancy or somehow? It might be a silly question. I don't know. So for example, because if you use 4 CPUs or 100 CPUs, for example, right? So there might be some, and especially on a very inhomogeneous, I guess, materials that will matter, or with multi-domains or something like that. Or am I asking something completely out of, yeah.
Sorry, I mean, no, I just didn't quite follow your question.
Is there a control over the decomposition? So how the decomposition is actually, how the pluralization is happening? Like for example,
I see. So you're okay. So in most terminology, that is called partitioning. So
okay.
you're asking how you want to partition your computational mesh into different like associate different partition with different tracks basically. So that's that's controllable. That's well. So I would encourage you to watch the Moose framework training if you have some time. That will be really helpful. But for now, there is a what is it? Yeah, there is a partitioner block. It actually, you have control over how Moose partitions your mesh and assigns each of the partition to different rank. So I think the default is do you know what's the default when or yeah, but yeah, I'm not sure I see that here, but maybe that's the default partitioner, and you have other choices. The commonly used one is a single rank partitioner. If you want to, well, that's for some stochastic tools application. If you want to put all of the computation onto a single processor, you have the random partitioner, the grid partitioner. So for example, if you know that you know a particular Cartesian grid of your mesh is expansive, you can sort of arrange so that the corresponding grid is smaller, so that you have better load balancing across different processors.
Mm-hmm. Okay, cool, nice.
Yeah, I think that partitioner information is available upfront in here. Let me check.
Yeah, Gary, I'm not sure off the top of my head what the default is. I could look it up. I guess I think it uses Parmenas through.
Yeah, it is.
Yeah, okay.
Yeah, correct. Okay. Yeah,
the default is. I mean, partitioning is NP hard, so it's, I don't think there's a so-called best solution out there.
Yeah. No, but yeah, thank you. Yeah, that you actually foresee my next question regarding the recommendation for joining the Moose. You say it's a Moose framework fundamentals. That's a course. I mean, I guess a workshop you recommend.
Yeah, so we do keep track of past and upcoming training here. So this one is the solid mechanics workshop. We focus on solid mechanics, but there are other ones that's called framework fundamentals. If you want to get a better overview of the the framework level capabilities, such as partitioning and recovering and restart.
Yeah, great. Thank you. Thank you. Thank you.
Okay, so if there's no more question, I think I can wrap up the workshop. And if you I don't well, so this is actually the first time I publicly give some tutorial on Nemo2. So if you're interested in Nemo2, you can let me know, and if I guess I'll gauge the interest in hosting another Nemo2 workshop on its own. Well, and well, in case you're interested, I do have the set of Nemo2 training slide if you want to take a look on your own. I can share the link with everyone after the workshop. So to wrap up the workshop, so yesterday we covered most of the fundamental capabilities of the Moose solid mechanics module, all the way from small, large deformation kinematics to homogenization constraints, structural dynamics, and time integration. So today we have implemented a multiphysics model coupling, solid mechanics with phase field to solve a phase field fracture problem. And an important takeaway is the strategies for setting up multiphysics coupling should be similar regardless of what types of problem you're looking at. So hopefully, so even though we only use the phase field fracture as the example for this workshop, you can find some useful strategies for your own type of problems that you're interested in. Yeah, and then this is not a small accomplishment. So everyone knows, we've essentially implemented an application that can solve phase field fracture problem from scratch within 2 days. What's next? You can stay up to date by following the most news. Well, so I'll open the link here. So we send out a newsletter about new capabilities and bug fixes every month. So make sure you can, if you want to stay up to date, come back to this page often. I've mentioned this earlier today. We have a discussion forum hosted on GitHub. If you have general research question that you want to use Moose to solve, or you have maybe questions regarding specific implementation, that is the go-to place. And if you have, for bug reports and feature requests, we use the GitHub issue tracker for those. And once you have built, I mean, hopefully at this point, everyone is comfortable with building your own application. So once you have built your own application, feel free to show off some cool results, and we're very happy to include that in the gallery page. So it helps people. I think it helps your research work to gain some attention from the broader community, and I think it's also a very nice means of telling other people in the community that, hey, my app can do this, so come use my app and we can collaborate. Well, so this is, I don't remember if I've shown this gallery page earlier, but this is what it looks like currently. So as you can see, there's a large number of multiphysics problems that we can solve. And the last sub-bullet point here is to help us make moves better by sending us your contribution. So when you implement your, when you build your own application, oftentimes you may find that certain capabilities missing from the framework. It's often recommended to first experiment that in your own application. And once you think that's working robustly and you think that implementation can benefit the community in general, we very welcome you to send us either patches or pull requests so that we can integrate that into the Moose code base so that everyone will have access to. Last but not the least, don't forget to cite us. I think I know Ben is probably here at some point. We should write a paper documenting solid mechanics, so that the solid mechanics module, so that people can hopefully properly cite us. With that, that's everything I want to cover in this workshop. And thank you very much for joining this workshop. And if you have any further questions, feel free to leave a message in the Slack workspace that will stay active in the next few weeks, I would say. Thanks, everyone. I will stop video recording now.
Thank you so much, Gary.